These are the answers to the AP Chemistry packet that covers topics 9.8 to 9.11. On this slide, you can see Unit 9 at a glance. Unit 9 is entitled Thermodynamics and Electrochemistry. In this video, we will take a look at topic 9.8, Galvanic and Electrolytic cells, topic 9.9, Cell potential and free energy, topic 9.10, Cell potential under non-standard conditions, and topic 9.11, Electrolysis and Faraday's law. In the video description area, there is a link to the AP Chemistry course and exam description, which we call the CED for short, and there is also a link to the packet that accompanies this video. Topic 9.8, Galvanic and Electrolytic cells. Here are some essential knowledge statements from the AP Chemistry course and exam description. Each component of an electrochemical cell, electrodes, solutions in the half cells, salt bridge, voltage or current measuring device, plays a specific role in the overall functioning of the cell. The operational characteristics of the cell, galvanic versus electrolytic, direction of electron flow, reactions occurring in each half cell, change in electrode mass, evolution of a gas at an electrode, ion flow through the salt bridge, can be described at both the macroscopic and particulate levels. Galvanic cells, sometimes called Voltaic cells, involve a thermodynamically favored reaction, whereas electrolytic cells involve a thermodynamically unfavored reaction. Visual representations of galvanic and electrolytic cells are tools of analysis to identify where half reactions occur and in what direction current flows. For all electrochemical cells, oxidation occurs at the anode and reduction occurs at the cathode. Now, before we take a look at question 1 in this packet, here is a short video of an experiment.
Remember that redox reactions are spontaneous in only one direction. Here we have an example of one spontaneous and one non-spontaneous redox reaction. First, we have the reaction of zinc metal with copper ion, then the reaction of copper metal with zinc ion. Let's see which one is spontaneous. As you can see, the zinc metal turned dark due to the formation of solid copper on the surface. For the zinc and copper metal reaction, there was no reaction.
So now that you've seen the results of the experiment, let's take a look at question number 1 in your packet. Question 1 says, a student places a strip of zinc metal into a solution of 1.0 molar copper 2 sulfate. The student also places a strip of copper metal into a solution of 1.0 molar zinc sulfate. The student's observations are shown in the table below. Part A. Based on the results of this experiment, classify each of the following reactions as thermodynamically favored or unfavored. So when zinc is placed in a solution of aqueous copper sulfate, a dark solid appears on the surface of the zinc. The color of the copper sulfate solution changes from dark blue to light blue. So that is evidence that a chemical reaction did occur. Therefore, that reaction would be classified as thermodynamically favored. Often in chemistry, when a reaction is thermodynamically favored in one direction, then it would be thermodynamically unfavored in the opposite direction. So when copper is placed in a solution of zinc sulfate, it appears that no chemical reaction occurred. Therefore, that reaction would be classified as thermodynamically unfavored. All right, now let's take a look at part B of this question. Write the net ionic equation for the reaction that you classified as thermodynamically favored. So we have solid zinc reacting with aqueous copper sulfate to produce aqueous zinc sulfate and solid copper. Now, when you are given a chemical equation and you have to write the net ionic equation, A question that you often have to ask is, do I split up the chemical formula into separate ions or leave it unchanged exactly as written? So we have both copper sulfate, CuSO4, and zinc sulfate, ZnSO4. Since these represent aqueous ionic compounds, then we will split them up into separate ions. And the charge on copper happens to be 2+. This is copper 2 sulfate, so the Roman numeral 2 means the charge on copper is +2. And the charge on the polyatomic ion sulfate, SO4, happens to be -2. So on the other side of the equation, we're going to split up zinc sulfate for the same reason. We have an aqueous ionic compound. Now that we have split up both the copper sulfate and the zinc sulfate, you can recognize the so-called spectator ion on both sides of the equation. So we're going to cross off the sulfate ion on both the left and the right side of the equation. And now what we get is the net ionic equation. So in this net ionic equation, it's going to be solid zinc reacting with aqueous copper 2+ ions to produce aqueous zinc 2+ ions and solid copper. Now on to part C of this question. In the equation that you wrote in part B, identify the species that is oxidized and the species that is reduced. Let me go back and show you a slide from an earlier video back in Unit 4. This is topic 4.7, types of chemical reactions. And highlighted on this slide is that oxidation-reduction reactions, also known as redox reactions, involve the transfer of one or more electrons between chemical species, as indicated by changes in oxidation numbers of the involved species. So here, another slide from an earlier video says that if the oxidation number increases, the element is oxidized, and if the oxidation number decreases, the element is reduced. Now let's go back and take a look at part C of this question. Zinc is changing from 0 to +2 in terms of its oxidation number. So zinc is oxidized from 0 to +2, and then copper is changing from +2 to 0. So copper is being reduced from +2 to 0. So this chemical reaction, which is classified as thermodynamically favored, in which electrons are transferred from zinc to copper, can be used to set up what is known as a galvanic cell. Let's take a look. A galvanic cell, also known as a voltaic cell, can be constructed that is based on the thermodynamically favorable reaction from question 1. So in this diagram, we see a strip of zinc metal in a solution of 1.0 molar aqueous zinc sulfate. We see a strip of copper metal inserted in a solution of 1.0 molar aqueous copper sulfate. We see a wire that connects the zinc strip to the copper strip. We also see a voltmeter in the middle, and that voltmeter registers a voltage of positive 1.10 volts. We see that the zinc metal has been labeled as the anode. The copper metal has been labeled as the cathode. We also see a salt bridge that is connecting the two beakers of solution. And if you look closely at the wire, you will notice that there are arrows along the wire. The arrows represent the direction of electron flow through the wire. So the electrons are flowing through the wire from the anode to the cathode. Now in the salt bridge, there are aqueous ions, but it's important that you understand electrons do not flow through the salt bridge. Ions are flowing in the salt bridge, and the ions flow in a particular direction, which I will explain. Now, in this example diagram of a galvanic cell, it just so happens that the zinc anode is located on the left side of the diagram, and the copper cathode is located on the right side of the diagram. But there's no rule in chemistry that the anode will always be on the left. So on the AP Chemistry exam, if you are given a galvanic cell diagram, you cannot assume that the anode is always on the left side of the diagram. So what you have to do is simply pay attention to the specific information given in the problem. And you're going to see several examples in this packet, in this video, of galvanic cell diagrams. And I will teach you what you need to look at as far as specific information to determine which electrode is classified as the anode and which electrode is classified as the cathode. Now what I'd like to do is to examine specific features of this galvanic cell, which will help you in general to understand how a galvanic cell works. So the features of this galvanic cell include the following. Oxidation occurs at the anode. So at the anode, zinc is losing electrons. It's being oxidized from 0 to +2. Reduction occurs at the cathode. So in this galvanic cell, copper ions are gaining electrons and copper is being reduced from +2 to 0. And as I had mentioned earlier, electrons flow through the wire in a particular direction. So electrons travel from the anode, where oxidation occurs, toward the cathode, where reduction occurs. And you can see in the diagram the arrows along the wire to indicate the direction of electron flow from the anode to the cathode. As the reaction in this galvanic cell proceeds over time, the mass of the zinc electrode, the anode, decreases because atoms of solid zinc are converted into aqueous zinc 2+ ions that enter the solution. So in this particle diagram, you can see a close-up view of what's happening at the anode. In the anode half cell, zinc atoms are converted into zinc 2+ ions, which dissolve and enter the solution. As the cell operates, the mass of the zinc anode decreases. Electrons are released in this oxidation reaction and flow through the wire from the anode toward the cathode. The mass of the copper electrode, the cathode, increases because aqueous copper 2+ ions are converted into solid copper atoms that are deposited on the surface of the cathode. So in this particle diagram, you can see a close-up view of what's happening at the cathode. In the cathode half cell, copper 2+ ions gain electrons that have traveled from the anode to the cathode. Aqueous copper 2+ ions are converted into copper atoms, which are deposited on the cathode. And as the cell operates, the mass of the solid copper cathode increases. The salt bridge is an essential component of a galvanic cell. It is often a tube filled with an aqueous solution of an electrolyte. This can be aqueous potassium nitrate or aqueous sodium sulfate or any ionic compound that does not react with the reactants or the products. If the salt bridge is removed, the voltage drops to 0. The purpose of the salt bridge is to allow ions to flow into each half-cell container in order to balance the overall charge in each container. Electrons do not flow through the salt bridge. Ions flow through the salt bridge. Cations move toward the cathode, and anions move toward the anode. In this particle diagram, you can see a close-up view of what's happening inside the salt bridge. Remember that electrons do not flow through the salt bridge. The cations, which are the positive ions, move toward the cathode, which is in the reduction half cell. Anions, which are the negative ions, move toward the anode, which is in the oxidation half cell. The movement of ions in the salt bridge occurs in order to balance the overall charge in each half-cell container. Now, let's take a look at a zoomed-in view of what happens in the anode half-cell container. So at the anode, oxidation occurs. Here we have an atom of zinc losing 2 electrons as it is converted into a zinc 2+ ion. So it enters the solution. Electrons that are lost in this oxidation reaction travel through the wire from the anode to the cathode. As the galvanic cell runs, cations are produced in this anode half-cell container. Positive ions, or cations, are produced in the anode half-cell container, and this causes a buildup of positive charge. So that's why the anions move toward the anode. In order to maintain a balance, of the overall charge in the anode half cell, the anions or negative ions from the salt bridge move toward the anode. Now let's take a look at a zoomed in view of the cathode half cell container. So here we see a copper 2+ ion moving toward the solid copper cathode. Remember that electrons travel through the wire from the anode to the cathode. So the cations in the cathode half cell container gain electrons to form atoms, and these atoms are deposited on the cathode. So here's another example of a copper 2+ ion gaining electrons to form a copper atom. So here's what happens as the cell runs over time. So as the galvanic cell runs, cations are consumed in the cathode half cell container. Positive ions are consumed in the cathode half cell container, and this causes a loss of positive charge. So in order to maintain a balance of the overall charge in the cathode half cell, the cations or positive ions from the salt bridge move toward the cathode. So to summarize the salt bridge ion movement, anions move toward the anode in order to balance the buildup of positive charge in the anode half cell. Cations move toward the cathode in order to balance the loss of positive charge in the cathode half cell. Now, before we take a look at question 2 in the packet, here is a mnemonic device that might help you remember which type of reaction occurs at which electrode. So whether it's a galvanic cell or an electrolytic cell, oxidation always occurs at the anode, reduction always occurs at the cathode. So the two animals on this slide, one of them is an ox and the other is a red cat. So an ox helps you remember that anode, oxidation, and then red cat helps you remember reduction, cathode. Now let's take a look at the diagrams that go along with question 2 in the packet. In the top diagram, we see a container, and inside the container is water and an electrolyte. There are two upside-down test tubes, and we can see that bubbles of gas are being produced inside each test tube. There is a wire, and the wires are connected to a DC voltage supply, which is essentially a battery. In the bottom diagram, we have a container, and in the container is molten or melted magnesium chloride, MgCl2. We also see a power source, which is essentially a battery, connected by a wire to two different electrodes. At one electrode, liquid magnesium is being produced, and at the other electrode, chlorine gas, Cl2, is being produced. So here's question 2. Experimental setups for two different electrolytic cells are shown above. Part A, identify a specific item that is included in each setup that supports the fact that the reaction that occurs in the electrolytic cell is not thermodynamically favored. So the difference between a galvanic cell and an electrolytic cell is that with a galvanic cell, the chemical reaction just happens naturally, it's thermodynamically favored, but in an electrolytic cell, the reaction that occurs is not thermodynamically favored. So it's the presence of that battery, it's the presence of that external power source that explains that this reaction that is occurring in the electrolytic cell does not happen unless an external power source or a battery is used in order to make that reaction occur. All right, now let's take a look at part B and part C. This is a review of oxidation-reduction reactions and changes in oxidation number. So for part B, complete each sentence based on the redox equation shown above. So we can see that water is the reactant, and the products are hydrogen gas and oxygen gas. So in water, the oxidation number for hydrogen is +1, and the oxidation number for oxygen is -2. But on the right side of the equation, since we have elements, hydrogen and oxygen, the oxidation number for hydrogen and oxygen as elements is 0. So what's happening is that hydrogen is changing from +1 to 0. Oxygen is changing from -2 to 0. Remember that when the oxidation number increases, we call that oxidation. So since oxygen is changing from -2 to 0, that is being oxidized. And when the oxidation number decreases, we call that reduction. So hydrogen is being reduced from +1 to 0. Now, I showed you that mnemonic device earlier to remember which type of reaction happens at which electrode. And that was an-ox and red cat. So anode, oxidation, reduction, cathode. So at the anode, oxygen is being oxidized from -2 to 0. And at the cathode, hydrogen is reduced from +1 to 0. Now for the other diagram, it's also an example of an electrolytic cell, but now we have magnesium chloride on the left, and we have magnesium and chlorine on the right. So what happens is that in magnesium chloride, the oxidation number of magnesium is +2, and the oxidation number of chlorine is -1. But on the right side of the equation, we have the elements, magnesium and chlorine, and their oxidation states for the elements would be 0. So magnesium is changing from +2 to 0. Chlorine is changing from -1 to 0. So remember that oxidation involves the increase in the oxidation number. So chlorine is oxidized from -1 to 0. And then reduction involves the decrease of the oxidation number. So magnesium is reduced from +2 to 0. So an-ox and red cat help you remember that oxidation occurs at the anode and reduction occurs at the cathode. Now, before we take a look at question 3 in the packet, I would like to do a little compare and contrast between a galvanic cell, also known as a voltaic cell, and an electrolytic cell. So the first feature is thermodynamic favorability. The chemical reaction that occurs in a galvanic cell is classified as thermodynamically favorable. On the other hand, the chemical reaction that occurs in an electrolytic cell is classified as thermodynamically unfavorable. So how is electrical energy involved in this type of reaction? Well, in a galvanic cell, you can think of this as a battery because this chemical reaction produces electrical energy. On the other hand, in an electrolytic cell, electrical energy from an external power source, for example, a battery, is actually required in order for this chemical reaction to occur. With respect to the change in free energy, or delta G, for the chemical reaction, in a galvanic cell, because it is a thermodynamically favorable reaction, the sign of delta G is negative. And with an electrolytic cell, because it is a thermodynamically unfavorable reaction, the sign of delta G is positive. And then something we'll talk about more in this video is called cell potential, which has the abbreviation capital E, or the voltage. For a galvanic cell, the sign of the cell potential is positive. Whereas in an electrolytic cell, the sign of the cell potential is negative. And then for either of these type of cells, whether it's galvanic or electrolytic, oxidation always occurs at the anode, and reduction always occurs at the cathode. With respect to the direction of electron flow in the wire, electrons are traveling through the wire from the anode to the cathode in a galvanic cell. And it's a similar process with an electrolytic cell. Even though there is an external power source or a battery, electrons are still traveling in that same direction through the wire from the anode and then to that power source and then on to the cathode. So it's the same direction of electron flow from the anode to the cathode. And as far as the number of containers, for a galvanic cell, you typically have two separate containers. You have the anode half cell, in which oxidation occurs, and then you have the cathode half cell, in which reduction occurs. For an electrolytic cell, the anode and the cathode are often in the same container. And with respect to a salt bridge, for a galvanic cell, a salt bridge is required, but for an electrolytic cell, a salt bridge is not required. All right, now let's take a look at question 3 in the packet. In question 3, it says, a student sets up a galvanic cell with a solid chromium electrode immersed in a 1 molar solution of aqueous chromium 3+ ions and a solid silver electrode immersed in a 1 molar solution of aqueous Ag or silver plus ions, as shown in the diagram at right. Part A. The student measures the voltage in the cell shown at right and discovers that it is 0. Identify the missing component of this cell. And you may have already guessed if you compare this diagram with the diagram that I showed you earlier in the video. There is a salt bridge, and that salt bridge is an essential component of a galvanic cell. If the salt bridge is removed, the voltage drops to 0. So what is the purpose of the salt bridge? Remember that electrons do not flow through the salt bridge. The purpose of the salt bridge is to allow ions to flow into each half-cell container in order to balance the overall charge in each container. So the answer to part A, the missing component is the salt bridge. And the answer to part B, what is the main purpose of the missing component that you chose in part A? The purpose of the salt bridge is to allow ions, not electrons, ions, to flow into each half-cell container in order to balance the overall charge in each container. Now, let's move on to part C of question 3. In part C, it says the student adds the missing component to the cell. A voltmeter is used to measure the standard cell potential, which is recorded as positive 1.54 volts. As the cell operates, the mass of the solid silver electrode increases. Based on this information, write the balanced net ionic equation for the overall chemical reaction that occurs as the galvanic cell operates. So because we know that the mass of the solid silver electrode increases, that means that the change for the silver is from aqueous silver ions to solid silver atoms. Because the mass of the silver electrode increases, we have to produce solid silver as a product. Now, that means that reduction is taking place in that silver container. So silver is being reduced from +1 to 0. And the opposite of reduction is oxidation. So now we know that in the other container involving chromium, there needs to be oxidation. So chromium is changing from 0 to +3. So that's oxidation. So we would show chromium starting on the left as a solid and then finishing on the other side of the equation as aqueous chromium 3+ ions. All right, so now we're almost done with this equation. And the reason why we're almost done is because even though we have balanced this equation in terms of atoms, we have not balanced this equation in terms of the overall charge. So if you look closely, you realize that there is a charge of +1 on the left, but there's a charge of +3 on the right. That's an important point, that this equation is not balanced in terms of the overall charge. So to finish off this equation, to balance it correctly in terms of both atoms and charge, we have to add a coefficient of 3 in front of the silver ion on the left, and then obviously a 3 in front of the silver atoms on the right. So now this equation is officially balanced in terms of both atoms and charge. All right, now let's take a look at question 4 in the packet. It says, a student sets up a standard galvanic cell with a solid copper electrode immersed in a solution of 1 molar aqueous copper nitrate and a solid tin electrode immersed in a solution of 1 molar aqueous tin nitrate. Now you may remember that earlier in this video, I had said that on the AP Chemistry exam, if you were given a diagram of a galvanic cell, do not automatically assume that the anode will be on the left in the diagram. So here's a good example. We have to use the information that we are given in this question to decide which electrode is the anode and which electrode is the cathode. So it says, as the current flows through the cell, the student determines that the mass of the copper electrode increases and the mass of the tin electrode decreases. So if the mass of the copper electrode increases, that means that in that copper container, the change is from aqueous ions to solid copper atoms. That's why the mass increases. And then on the other side, in the tin container, since the mass of the tin electrode decreases, then the change must be from atoms of tin to aqueous tin plus ions. So it turns out that in part A, when it says identify the electrode that represents the anode and the electrode that represents the cathode, you cannot assume that the anode is always going to be on the left. It depends on the diagram and the specific information. So here we can see that oxidation always occurs at the anode, reduction always occurs at the cathode. So for the anode, that would be the site of oxidation. That's when tin is changing from 0 to +2. So that makes tin the anode. And then for the cathode, looking for reduction, that would be copper changing from +2 to 0. So copper is the cathode. All right, now let's move on to part B of this question. We already know what the half reactions are at each electrode. So for part B, write the net ionic equation for the half reaction that occurs at each electrode. So the half reaction that occurs at the anode would be the oxidation, where tin changes from 0 to 2+, so the loss of 2 electrons. And the half reaction at the cathode is the reduction, where copper is changing from +2 to 0, and that's gaining 2 electrons. Now, the next question, part C, says on the diagram above, draw an arrow to indicate the direction of electron flow in the wire as the galvanic cell operates. So because electrons are being lost at the anode, and because electrons are being gained at the cathode, that tells us the direction in which electrons flow in the wire. So electrons flow through the wire, and they travel from the anode, where oxidation occurs, toward the cathode, where reduction occurs. So I'll go ahead and draw the arrow from the anode toward the cathode, like this. And now the next part of this question says to look at the salt bridge. It says a solution of sodium sulfate, Na2SO4, is used in the salt bridge. In the expanded view of the center portion of the salt bridge, shown in the diagram at right, draw and label a particle view of what occurs in the salt bridge as the cell begins to operate. Omit solvent molecules, so you don't have to draw any water molecules, and use arrows to show the direction of movement of the particles. Remember that electrons do not flow through the salt bridge. Ions flow through the salt bridge, and since cations move toward the cathode and anions move toward the anode, we're going to draw the positive ion, which would be the sodium ion, moving toward the left, toward the cathode in this diagram, and then we'll draw the negative sulfate ion, the SO4 2- ion, moving toward the right, toward the anode. So cations toward the cathode, anions toward the anode. Again, don't assume that the anode will always be on the left. Look at the specific information that you were given in a galvanic cell diagram and how they discuss what's happening in that galvanic cell. All right, now let's take a look at question 5 in the packet. Hopefully you can tell that there is a difference between the diagram in question 5 and the diagram in question 4. So in question 4, it was an example of a galvanic cell. Here in question 5, you can see this is going to be an example of an electrolytic cell. And the difference is that there's that power supply, that external power supply or a battery that is required in order for the chemical reaction in an electrolytic cell to occur. All right, so question 5 says the following. An external direct current power supply is connected to 2 platinum electrodes immersed in a beaker containing 1 molar aqueous copper sulfate at 25 degrees Celsius, as shown in the diagram above. As the cell operates, copper metal is deposited onto one electrode, and oxygen gas is produced at the other electrode. 2 reduction half reactions are listed in the table below, along with the value of the standard reduction potential for each half reaction. Part A. Is the overall chemical reaction that occurs in this electrochemical cell classified as thermodynamically favored or unfavored? Justify your answer. So it's that external power supply that really gives it away in this diagram. So remember that for an electrolytic cell, this is a thermodynamically unfavorable reaction in which electrical energy from an external power source, for example a battery, is required in order for this chemical reaction to occur. So that's going to be our answer to part A of this question. The chemical reaction that occurs in this cell is thermodynamically unfavored because an external power supply is needed in order for the reaction to occur. Now, let's take a look at part B of this question, in which you have to decide if the cell potential for the overall chemical reaction that occurs in this electrochemical cell is positive or negative. So earlier in the video, when I was doing that compare and contrast between a galvanic cell and an electrolytic cell, I said that the cell potential for an electrolytic cell is negative. And so the answer to part B is negative, and that's because an external power source is required in order for this reaction to occur. That's why the cell potential will be negative for this chemical reaction. All right, let's move on to part C of this question. It says write the net ionic equation for the half reaction that occurs at each electrode. Now we are given 2 reduction half reactions in the table. Let's take a look at what's happening at each electrode, and then we can process which electrode is the anode and which electrode is the cathode. So in the diagram, it says that solid copper is deposited onto the electrode on the left. In the table, where there are 2 half reactions listed, I see that solid copper is produced from aqueous copper 2+ ions. So that reaction that I'm highlighting on this slide, that is the reaction that is occurring in the electrode on the left in this diagram. Now, for the other half reaction, it does involve oxygen gas, but you'll notice that it says that oxygen gas is being produced at the electrode on the right in the diagram. And in the table, it shows that oxygen gas is featured as a reactant and not a product. So that gives us a clue that that half reaction must be reversed. So since we know that oxygen gas is produced at the electrode on the right in the diagram, then this equation should be reversed. So I'm going to go ahead and flip that equation around so it shows that 2 moles of liquid water react to produce 1 mole of oxygen gas plus 4 moles of aqueous H+ ions plus 4 moles of electrons. Another reason that I needed to flip one of these equations is that in this electrochemical cell, there must be an oxidation reaction and a reduction reaction. So you can't have 2 reduction reactions happening at the same time. So one of those equations had to be flipped around or reversed. Now, we still haven't answered part C, but now at least we know what reaction is taking place at each electrode. So what I know so far is that the reaction involving the formation of solid copper is an example of a reduction reaction in which electrons are gained, and that the other reaction that involves the formation of oxygen gas is an example of an oxidation reaction in which electrons are lost. So what I have to do now is remember that mnemonic device. So oxidation occurs at the anode, reduction occurs at the cathode. So in this diagram, the reduction reaction that involves the formation of solid copper, so that electrode that happens to be on the left would be labeled as the cathode. And then the oxidation reaction that involves the formation of oxygen gas, that electrode will be labeled as the anode. So now that I've identified which reaction is occurring at which electrode, and I've identified which electrode is the cathode and which electron is the anode, I can now answer part C very easily. So the half reaction that occurs at the anode involves the formation of oxygen gas, which is just that reversed half reaction from the table. And the half reaction that occurs at the cathode involves the formation of solid copper. And that was the half reaction from the table that I did not reverse, that I used exactly as written. So as we can see in our answer to part C, we have two half reactions. We have the oxidation half reaction that occurs at the anode involving the formation of oxygen gas. And we have the reduction half reaction that occurs at the cathode involving the formation of solid copper. So what do you do with these two half reactions? Well, we can add them together to give us the overall equation for the redox reaction that occurs in this electrolytic cell. So that's the process in part D. It says when combining two different half reactions to produce the overall equation for a redox reaction, the total number of electrons gained should be equal to the total number of electrons lost. Use the information from the table above to write a balanced net ionic equation for the chemical reaction that occurs in this electrochemical cell. So I have to combine these two half reactions together. We have the reduction reaction involving the gain of electrons, and we have the oxidation reaction involving the loss of electrons. And you may already have noticed the problem in that in our reduction half reaction, it involves the gain of 2 electrons. In our oxidation half reaction involves the loss of 4 electrons. So what we have to do before we can combine these two half reactions together is we have to make sure that the electrons will cancel out on opposite sides of the equation. So what I'm going to do is multiply the reduction half reaction by 2 in order to get the electrons to cancel out. Now when I multiply that equation by 2, now my coefficients from left to right become 2, 4, and 2. I'm going to go ahead and add these two half reactions together, and now I can see that the electrons that are gained in the reduction half reaction are equal to the electrons lost in the oxidation half reaction. So when I add these two equations together, I get 2 moles of aqueous copper 2+ ions plus 2 moles of liquid water to produce 2 moles of solid copper plus 1 mole of oxygen gas plus 4 moles of aqueous H+ ions. So that overall chemical equation is the answer to part D. Now, let's move on to part E of this question. Part E says to calculate the value of the standard cell potential in volts for the chemical reaction that occurs in this electrolytic cell. Now, the skills that you need to answer this question will also be explained when we get to the next topic, which is topic 9.9, cell potential and free energy. So in a sense, answering this particular question is really a preview of the concepts that you will see in our next topic, topic 9.9. So here you can see on this slide, there are several guidelines for manipulating half reactions. The first one I'm going to highlight is this one, which says, when combining two different half reactions to produce the overall equation for a redox reaction, the total number of electrons gained should be equal to the total number of electrons lost. Now, that was a concept that was important when answering part D of this question. But now in part E, we have to calculate the cell potential for the overall equation, the overall reaction. So another guideline that I want to highlight that's important is the following. It says if a half reaction is reversed, the sign of the cell potential is also reversed. So you may recall that we are given two different reduction half reactions in the table, and one of them did have to be reversed. We had discovered earlier in this problem that since oxygen gas is produced at one of the electrodes in this electrolytic cell, it meant that that first half reaction that was given, which shows oxygen or O2 as a reactant, we had to flip it, we had to reverse it. So look at what I did on this slide. Not only did I change the order of the reactants and the products, so now it says 2H2O on the left and O2 plus 4H plus 4 electrons on the right. Look at what I did to the sign of the cell potential when I reversed this half reaction. So in the table, it said the cell potential was positive 1.23, and now because I reversed that equation, the cell potential is actually negative 1.23 volts. All right, the next set of guidelines I'd like to highlight are these last two statements here on this slide. It says, multiplying a half reaction by a constant n does not change the value of the cell potential. That's an important concept, and it looks a little bit confusing because you might wonder, well, don't we double everything, including the cell potential? But here's the reason why we do not change the value of the cell potential. It has to do with the units. So by definition, 1 volt is equal to 1 joule per coulomb. And the joule is a unit of energy. And the coulomb is a unit of electrical charge. And so if a half reaction is multiplied by a constant n, then what happens is that both the joules and the coulombs are each multiplied by that same factor n. So therefore the ratio of joules per coulomb, or volts, remains the same. And so the value of the cell potential, which is also known as the voltage, remains the same. So that is the reason. It's because of the units and the fact that that ratio is doubled. That's the reason why when the value of the cell potential is not multiplied by n, when a half reaction is multiplied by n. So watch what happens here. Remember that earlier in this problem, we discovered that the electrons lost, which are 4 electrons in the oxidation half reaction, had to be equal to the electrons gained in the reduction half reaction. So you may recall that earlier we had to multiply that copper half reaction by the number 2 to get the electrons to balance or to cross out on opposite sides of the equation. So look at that new manipulated half reaction. Now the coefficients are 2, 4, and 2, but you'll notice that the cell potential remains at positive 0.34 volts. So even though we multiplied each and every coefficient of that half reaction by 2, we did not multiply the cell potential or the voltage by the number 2. All right, so earlier in part D, we had to add these two equations together. And as you can see, the electrons gained in the reduction half reaction are the same as the electrons lost in the oxidation half reaction. So there's our overall equation. That was the answer to part D. So what about the cell potential? It's going to be the sum of the cell potentials for the two half reactions added together. So I have a positive 0.34 volts plus a negative 1.23 volts. So when you do that math, that combination of 0.34 plus a negative 1.23, you get a value of negative 0.89 volts. So that is the answer to part E of question 5 in the packet. Again, it was the manipulated half reactions. The first half reaction involving copper was multiplied by 2, but the cell potential did not change. The other half reaction was reversed, and the cell potential, its sign, was also reversed. So we got negative 0.89 volts. What's also nice about the answer to part E is it is a confirmation of the answer to part B. So earlier in this question, we had decided that because an external power source is required in order for the reaction in this electrolytic cell to occur, that the sign of the cell potential should be negative. And in fact, we got negative 0.89. So that's a confirmation of the answer to part B. All right, the last part here, part F, says on the diagram on the previous page, draw an arrow to indicate the direction of electron flow in the wire as the electrolytic cell operates. So earlier in this video, when I was doing that compare and contrast between a galvanic cell and an electrolytic cell, when talking about the direction of the electron flow in an electrolytic cell, electrons travel through the wire from the anode to the power source to the cathode. So those are the arrows that I will draw in the diagram. So I'm going to show that the arrow proceeds with electron flow through the wire from the anode to the power supply and then on to the cathode. So that is the direction of electron flow, which is the answer to part F. Okay, now we are ready to move on to our next topic in this packet. This is topic 9.9, cell potential and free energy. Here are some essential knowledge statements from the AP Chemistry course and exam description. Electrochemistry encompasses the study of redox reactions that occur within electrochemical cells. The reactions are either thermodynamically favored, resulting in a positive voltage, or thermodynamically unfavored, resulting in a negative voltage and requiring an externally applied potential for the reaction to proceed. The standard cell potential of electrochemical cells can be calculated by identifying the oxidation and reduction half reactions and their respective standard reduction potentials. Delta G, the standard Gibbs free energy change, is proportional to the negative of the cell potential for the redox reaction from which it is constructed. Thus, a cell with a positive cell potential involves a thermodynamically favored reaction with a negative value of delta G, and a cell with a negative cell potential involves a thermodynamically unfavored reaction with a positive value for delta G. Now, the last equation that you can see on this slide, the delta G is equal to negative N times F times the cell potential E. That equation is featured on the AP Chemistry equations and constant sheet. So we know that delta G is the change in the standard Gibbs free energy. The lowercase n represents the number of moles of electrons. The capital F is the Faraday constant. And you can see on the right side at the bottom of this slide, the Faraday constant has a value of 96,485 coulombs for every 1 mole of electrons. And of course, that E is the standard cell potential. So delta G is equal to negative N times F times E. And we'll see calculations of how to get the delta G in this section of the packet for topic 9.9. All right, so here are the guidelines that I had mentioned earlier when I was solving question 5 in the packet. These are the guidelines for manipulating half reactions. The standard cell potential is positive for the reaction that occurs in a galvanic cell. That's thermodynamically favored. The standard cell potential is negative for the reaction that occurs in an electrolytic cell, which is thermodynamically unfavored. When combining two different half reactions to produce the overall equation for a redox reaction, the total number of electrons gained should be equal to the total number of electrons lost. If a half reaction is reversed, the sign of the cell potential for that half reaction is also reversed. Multiplying a half reaction by a constant n does not change the value of the cell potential. And again, the reason for that is because of units. So by definition, 1 volt is equal to 1 joule per coulomb. And the joule is a unit of energy, and the coulomb is a unit of electric charge. So if a half reaction is multiplied by a constant n, both the joules and the coulombs are each multiplied by n. Therefore, the ratio of joules per coulomb, or volts, remains the same. And so the value of the cell potential, also known as the voltage, remains the same. And so this is the reason why the value of the cell potential is not multiplied by n when a half reaction is multiplied by n. And here you can see the equation that says 1 volt is equal to 1 joule per 1 coulomb. That equation is listed in the unit conversions section of the AP Chemistry equations and constant sheet. So now, here are some guidelines for calculations involving that equation that relates delta G and the cell potential. If the standard cell potential is positive, then the standard free energy change is negative. So we have a thermodynamically favored reaction. If the standard cell potential is negative, then the standard free energy change is positive, and we have a thermodynamically unfavored reaction. And the variable n in this equation represents the total number of moles of electrons transferred in the overall balanced equation for the redox reaction. As I mentioned, the Faraday constant is equal to 96,485 coulombs per mole of electrons. And in terms of units, 1 coulomb multiplied by 1 volt is equal to 1 joule. And then the last point to mention here is that the units of the delta G, the change in free energy, are usually reported in units of kilojoules per mole of reaction. So we'll see how you may have to divide by 1,000 when going from joules to kilojoules when you're using this equation to do calculations. All right, so this is question 6 in your packet. Question 6 says the following. A student sets up a standard galvanic cell with a solid aluminum electrode immersed in a 1 molar solution of aqueous aluminum nitrate and a solid zinc electrode immersed in a 1 molar solution of aqueous zinc nitrate. The standard reduction potential for each metal is listed in the table below. In part A, it says to write the balanced net ionic equation for the reaction that occurs as this galvanic cell operates. And part B says to calculate the value of the standard cell potential in volts for the chemical reaction that occurs in this galvanic cell. Now, since the answer to part A and the answer to part B are so closely related to each other, we can pretty much answer questions A and B at the same time. So let's take a look at the 2 half reactions that we are given in this table. We know that we have a galvanic cell, and therefore the standard cell potential should be positive for the reaction that occurs in a galvanic cell. So when the half reactions are added together to produce an overall equation, the sign of the cell potential should be positive. We also know that we are given 2 reduction half reactions. So we need an oxidation half reaction and a reduction half reaction. So therefore, one of these half reactions in the table must be reversed. So if you're not sure which half reaction to reverse, think about the fact that the overall cell potential should be positive. If a half reaction is reversed, the sign of the cell potential is reversed. So which equation we should reverse is the one that will give us a value that when added to the other cell potential for the other half reaction will still give us a positive value overall. So if we reverse the aluminum half reaction, it will change the cell potential from negative 1.66 volts to a value of positive 1.66 volts. Then when we add the cell potential for the reduction half reaction, which is the zinc, then when we add a positive 1.66 volts plus a negative 0.76 volts, it will give us a positive value overall. So that's how we knew to reverse the aluminum half reaction and then to keep the zinc half reaction as a reduction. We're trying to get a positive value overall when the 2 half reactions are added together. Now, the other thing we have to take a look at is the number of electrons gained equal to the number of electrons lost? So when combining 2 different half reactions to produce the overall equation for a redox reaction, the total number of electrons gained should be equal to the total number of electrons lost. So we can tell that since 2 electrons are gained in that zinc half reaction and 3 electrons are lost in that aluminum half reaction, the least common multiple of 2 and 3 is the number 6. So now we're going to multiply the aluminum half reaction by 2. So 2 times 3 is 6. And then we're going to multiply the zinc half reaction by 3, because 3 times 2 is 6. Remember that even though we are multiplying each of these half reactions by a constant, this does not change the value of the cell potential. So do not multiply the cell potential by either 2 or 3. Those values will remain the same. So now that I've multiplied through, I get 2 aluminum on the left, I have 2 aluminum on the right and 6 electrons. And in the other half reaction, I have 3 zinc, 6 electrons, and 3 zinc. Of course, when I add these two half reactions together, the electrons are going to cancel out. So my overall equation looks like the following. 2 solid aluminum, or 2 moles of solid aluminum, plus 3 moles of aqueous zinc 2+ ions, produces 2 moles of aqueous aluminum 3+ ions, and 3 moles of solid zinc. Now for the overall cell potential, it's going to be positive 1.66 volts plus negative 0.76 volts, and that gives us an overall cell potential, which is positive. It's positive 0.90 volts. So now we have answered both parts A and B of this question. So there's the answer to part A, the balanced equation for the overall reaction that occurs as this galvanic cell operates, and then the value of the overall standard cell potential for this reaction. So positive 0.90 volts. Again, it's positive because the reaction is thermodynamically favored. Now, on to part C of this question. You can see that now we have to calculate the value of the standard free energy change, or delta G, in units of kilojoules per mole of reaction. So I will show you that information that I had presented earlier, the guidelines for calculations involving the equation delta G equals negative N, which is the total number of moles of electrons transferred. It's going to be 6 in this case, times the Faraday's constant, which is 96,485 coulombs per mole of electrons, and then times the cell potential for the overall reaction, which is in units of volts. So a coulomb times a volt is equal to a joule. So there's our overall equation. There's my delta G equals negative N times F times the cell potential. So I've got my negative sign in the equation. So there's that negative sign. Don't forget that negative sign. That's important. I have 6 for the total number of moles of electrons that were transferred in the process of adding these two half reactions together. I've got my Faraday constant, 96,485 coulombs per mole of electrons. And then finally my cell potential, which is positive 0.90 volts. So the math that I did on my calculator is the following. It's going to be negative 6 times 96,485 times positive 0.90. So I got negative 521,019 without doing any rounding. As far as my units, it's going to be a coulomb times a volt is equal to a joule. So I'm going to convert this from joules to kilojoules. I'm also going to round this off to 2 significant figures, because looking at my numbers, 0.90, which is the cell potential, has 2 significant figures. And the number 6 is an exact number, so it has unlimited significant figures. The number 6 is counting the exact number of electrons transferred. So rounding this off to 2 significant figures, I get negative 520,000. And my units are actually joules per mole of reaction for this overall equation that we have. So negative 520,000 joules per mole of reaction. When I divide by 1,000 to go from joules to kilojoules, I get negative 520 kilojoules per mole of reaction. Now, what's nice about this is it reminds you that this reaction is thermodynamically favored. We have a positive cell potential, which is positive 0.90 volts, and we have a negative value for the delta G. So positive cell potential, negative delta G, that's consistent with the fact that a galvanic cell, the reaction that takes place in a galvanic cell, is thermodynamically favored. So the answer to part C is negative 520 kilojoules per mole of reaction. And that calculation is based on the relationship between the standard free energy change, delta G, and the overall cell potential for a redox reaction. Now, let's take a look at part D of this question. So it says in part D, in this voltaic cell, aluminum represents the, and we have to choose either anode or cathode, and it says the mass of the aluminum electrode will, and we have to choose either decrease or increase as the cell operates. So looking at the overall balanced chemical equation for this reaction, you can see that aluminum changes from an oxidation number of 0 on the left to an oxidation number of +3 in the aqueous ions that are produced on the right. So aluminum is oxidized from 0 to +3. That means that zinc is reduced from an oxidation number of +2 for the aqueous zinc ions on the left side of the equation, and now it is solid zinc on the right. That means oxidation number changes from +2 to 0. So if we know that aluminum is being oxidized and zinc is being reduced, remember that mnemonic device for what happens at each electrode in a galvanic cell. So oxidation occurs at the anode, reduction occurs at the cathode. That means that aluminum, which is the site of oxidation, is the anode, and zinc, which is the site of reduction, is the cathode. So in this voltaic cell, aluminum represents the anode. Now, what about the mass of the aluminum electrode? Well, if it's changing from atoms of aluminum to aqueous ions of aluminum that are being dissolved and released into the solution, then the overall mass of the aluminum electrode should decrease as the cell operates. Now, for the zinc, which is going to be the site of reduction, that's going to be the cathode, what's happening at that particular half cell is that aqueous ions of zinc are being converted into atoms of solid zinc that are going to be deposited on that electrode. So the mass of the zinc electrode will increase as the cell operates. So once we know what reactions are taking place at each electrode, then we can answer part D. Now, part E says on the diagram above, draw an arrow to indicate the direction of electron flow in the wire as the galvanic cell operates. So in a galvanic cell, as well as an electrolytic cell, electrons are always going to flow from the site of oxidation, where electrons are lost at the anode, to the site of reduction, where electrons are gained at the cathode. So electrons are flowing in the wire from the anode to the cathode. Now let's take a look at part F of this question. Here in part F, we have to draw a particle view of what occurs in the salt bridge as the cell begins to operate. So it says a solution of potassium nitrate, KNO3, is used in the salt bridge. In the expanded view of the center portion of the salt bridge shown in the diagram at right, draw and label a particle view of what occurs in the salt bridge as the cell begins to operate. Omit solvent molecules and use arrows to show the direction of movement of the particles. Remember that electrons do not flow in the salt bridge. We're focusing only on the movement of the ions. And the ions in this case are potassium, which is K+, and nitrate, which is NO3-. We know that the anode in this galvanic cell diagram is on the left. We know that the cathode in this galvanic cell diagram is on the right. We also know that anions flow toward the anode. So the nitrate ion, which is a negative ion, is flowing toward the anode. And we know that cations flow toward the cathode. So the positive K+ ion is flowing toward the cathode. All right, so that is the answer to part F. Now, let's take a look at our next question in the packet. This is question 7. In question 7, we're given the following information. It says a student wants to determine the concentration of H2O2, which is hydrogen peroxide, in a solution of aqueous hydrogen peroxide. The student can use one of two titrants, either dichromate ion, which is Cr2O7 that carries a -2 charge, or the cobalt-2 ion, which is CO that carries a 2+ charge. Now the balanced chemical equations for the two titration reactions are shown below. The half reactions and the standard reduction potentials for the systems related to the titrations above are listed in the following table. Now let's take a look at part A. In part A, it says use the information in the table to calculate the following. So for Roman numeral 1 of part A, it says to calculate the standard cell potential for the reaction between the dichromate ion and hydrogen peroxide. Now, we were already given the balanced chemical equation for the dichromate as titrant. What we have to do in this question is we have to pick two of the half reactions from the table, and then make whatever changes or modifications that are necessary so that when the two half reactions are added together, they will produce the overall balanced chemical equation that you see at the bottom of this slide. So this is the equation for the dichromate ion as titrant. The overall balanced chemical equation involves 1 mole of the aqueous dichromate ion reacting with 3 moles of aqueous hydrogen peroxide plus 8 moles of the aqueous H+ ion. And on the product side, we have 2 moles of aqueous chromium 3+ ions, 3 moles of oxygen gas, and 7 moles of liquid water. So that's my target equation. Now I'm going to go ahead and take a look at the table, and I see the first chemical that's listed as a reactant is the dichromate ion. So that third half reaction that is listed in the table has 1 mole of dichromate on the left as a reactant. That's exactly what I want in the overall balanced chemical equation. So I'm just going to rewrite that half reaction. I'm not going to change it at all. I'm not going to reverse it. I'm not going to multiply it by 2 because it has exactly what I need, which is 1 mole of dichromate on the left as a reactant. And since I didn't change that half reaction at all, the cell potential remains as positive 1.33 volts for that half reaction. Now, I'm looking for oxygen as a product. And in fact, I need 3 moles of oxygen gas as a product. So the only half reaction that involves oxygen gas, or O2, is this last one that's listed in the table. So the two things that I have to do to that half reaction to get 3 moles of oxygen gas produced as a product is I have to reverse that half reaction and I have to multiply that half reaction by 3. Now remember that when a half reaction is reversed, the sign of the cell potential is also reversed. But when you multiply a half reaction by a constant n, the value of the cell potential is not multiplied by that constant n. So take a look at the modified version of that half reaction after it's been reversed and multiplied by 3. So now we have on the left 3 moles of aqueous hydrogen peroxide. And on the right, we have 3 moles of oxygen gas, 6 moles of aqueous H+ ions, and 6 moles of electrons. And take a look at that cell potential. The sign of the cell potential did get changed from positive 0.70 volts to negative 0.70 volts. But I did not multiply the cell potential by 3 when I multiplied the coefficients by 3. All right, let's confirm that when these two half reactions are added together, they will give us the overall equation for this titration that we were given. So I can see that I have 6 electrons on the left and 6 electrons on the right, so I'm going to cross those off. I have 1 mole of dichromate, and I have 3 moles of aqueous hydrogen peroxide. Now, there are 14 moles of H+ on the left, and there are 6 moles of H+ on the right, so the difference between 14 and 6 is 8. So we do have 8 moles of aqueous H+ on the left. That is correct. And on the right side of the equation, we have 2 moles of aqueous chromium 3+ ions, 3 moles of oxygen gas, and 7 moles of liquid water. So it does work out. Let's go ahead and add the two cell potentials for these two half reactions together. So positive 1.33 volts plus negative 0.70 volts gives us a total for the overall cell potential for this equation of positive 0.63 volts. So that is the answer to part A, Roman numeral 1. Now I'm going to use the same process for part A, Roman numeral 2. So our overall equation for the titration between the cobalt-2 ion and hydrogen peroxide looks like this. You can see it on the bottom of this slide, 2 moles of aqueous cobalt-2+ plus 1 mole of hydrogen peroxide plus 2 moles of aqueous H plus ions produces 2 moles of cobalt 3 plus and 2 moles of liquid water. So the first chemical that I see that I'm going to focus on is the cobalt. Now, there's 2 moles of aqueous cobalt 2 plus featured as a reactant on the left in our overall target equation. And so looking at the first half reaction in the table, what I see is that the cobalt 2 plus ion is actually featured as a product, and I need it to be a reactant. So that equation is going to get reversed. I also need a coefficient of 2 for the cobalt. So this equation, this first half reaction, should be reversed and multiplied by 2. And so when I make that change, I am going to change the sign of the cell potential. So it's going to change from positive 1.84 volts to a value that is now negative 1.84 volts because I reversed the equation, but multiplying each coefficient by 2 did not affect the value of the cell potential. And I'm looking for hydrogen peroxide as a reactant. I'd also like to see liquid water as a product, so I'm going to pick the second half reaction. It has exactly what I want, which is 1 mole of H2O2 on the left as a reactant, so that is not going to be changed at all. So that cell potential remains unchanged as positive 1.77 volts. Let's confirm that when I add these two half reactions together, I get the overall balanced equation, which is the target that I was interested in. So I see 2 electrons on the left, and I see 2 electrons on the right, so I'm going to cross those off. And I see everything on the reactant side that's exactly what I want, which is 2 moles of cobalt 2 plus ions, 1 mole of aqueous hydrogen peroxide, and 2 moles of H plus aqueous ions. And on the right, I see 2 moles of cobalt 3 plus ions and 2 moles of liquid water. And the math involved for getting the cell potential for the overall balanced chemical equation would be negative 1.84 plus 1.77. So that works out to be negative 0.07 volts as the cell potential for the overall balanced equation in Part A, Roman numeral 2. Now, let's move on to Part B of this question. It says, based on the calculated values for the cell potential, which we got in Part A, the student must choose the titrant for which the titration reaction is thermodynamically favorable at standard conditions. So remember that a positive cell potential is favorable, but a negative cell potential is not favorable. So looking at our guidelines for using calculations involving the equation delta G and the cell potential, if the standard cell potential is positive, then the standard free energy change is negative and the reaction is thermodynamically favored. So as far as which titrant, the dichromate ion or the cobalt 2 plus ion, the student should choose, it's going to be the reaction that has a positive cell potential. So the student should choose the dichromate ion for the titration, because based on our answers to Part A, the value of the cell potential is positive for that titration reaction, and that means that the reaction is thermodynamically favorable. They should not choose the cobalt because the cell potential is negative, and that reaction would be thermodynamically unfavorable. So dichromate is the answer, positive cell potential, thermodynamically favorable reaction. Now let's take a look at the follow-up question, which says, calculate the value of the standard free energy change, delta G, in units of kilojoules per mole of reaction for the reaction between the chosen titrant and hydrogen peroxide. So to do this calculation, we know that the overall cell potential is positive 0.63 volts. So that's going to go into this equation. We know that with a positive cell potential, we should have a negative delta G, which indicates that the reaction is thermodynamically favored. So there's our equation. And from the combination of the two half reactions, we know that the total number of moles of electrons that were transferred is 6. So 6 electrons were gained in the reduction half reaction, and 6 electrons were lost in the oxidation half reaction. So there's that negative sign. Don't forget that negative sign. There's the number 6 for the 6 moles of electrons. And then from the equation sheet, we have the Faraday constant, which is 96,485 coulombs per mole of electrons. And the cell potential for this reaction is positive 0.63 volts. So on the calculator, if we do this math, negative 6 times 96,485 times positive 0.63, we get negative 364,713 without rounding it off yet. Coulomb times volt equals joule. So I'm going to turn this into kilojoules per mole of reaction by dividing by 1,000. I'm also going to round this off to 2 significant figures since 0.63 volts, the cell potential, has 2 significant figures. The number 6 is an exact number, so that does not limit the sig figs in the calculation. So it's going to be negative 360,000 joules per mole of reaction, or when I divide by 1,000 to go from joules to kilojoules, I get negative 360 kilojoules per mole of reaction. Again, that negative sign for the delta G reminds me that this reaction is thermodynamically favored. Okay, now it is time to move on to our next topic in this packet. This is topic 9.10, cell potential under non-standard conditions. Here are some essential knowledge statements from the AP Chemistry course and exam description. In a real system under non-standard conditions, the cell potential will vary depending on the concentrations of the active species. The cell potential is a driving force toward equilibrium. The farther the reaction is from equilibrium, the greater the magnitude of the cell potential. Equilibrium arguments, such as Le Chatelier's principle, do not apply to electrochemical systems because the systems are not in equilibrium. The standard cell potential, which is symbolized by the capital E with that superscript 0, looks like a degree symbol, the standard cell potential corresponds to the standard conditions of Q equals 1. And Q is the reaction quotient. That's a ratio of products over reactants for the aqueous components in electrochemical cells. And as the system approaches equilibrium, the magnitude, that is the absolute value of the cell potential, decreases, reaching 0 at equilibrium where Q, the reaction quotient, equals K, the equilibrium constant. Deviations from standard conditions that take the cell further from equilibrium than Q equal 1 will increase the magnitude of the cell potential relative to the standard cell potential. On the other hand, deviations from standard conditions that take the cell closer to equilibrium than Q equal 1 will decrease the magnitude of the cell potential relative to the standard cell potential. In concentration cells, the direction of spontaneous electron flow can be determined by considering the direction needed to reach equilibrium. Now, later in this video, I will talk about this particular diagram. So between questions 8 and 9 in the packet, I will spend more time talking about this diagram. You can see that there is a Q, which is this ratio of products over reactants for a chemical equation, a redox equation, and I'm highlighting Q equal 1 under standard conditions, Q greater than 1 closer to equilibrium than standard conditions, and Q less than 1 farther away from equilibrium than standard conditions. But again, I'll talk more about this later in the video between questions 8 and 9. And then the next essential knowledge statement says, algorithmic calculations using the Nernst equation are insufficient to demonstrate an understanding of electrochemical cells under non-standard conditions. However, students should qualitatively understand the effects of concentration on cell potential and use conceptual reasoning, including the qualitative use of the Nernst equation to solve problems. So at the bottom of this slide, you can see that's actually the Nernst equation right there. In question 9 in this packet, you will definitely have the opportunity to use conceptual reasoning and qualitative use of the Nernst equation to solve problems. So here on the AP Chemistry equation sheet, you can see that the Nernst equation is highlighted on the left, and the definition of Q, the reaction quotient, on the right, that is a ratio of products over reactants, kind of like an equilibrium constant, except it's Q because it's not at equilibrium. So when you see that E with a superscript 0, it looks like a degree symbol, that is the standard cell potential with that superscript 0. But then when you don't see that superscript 0, that would be the non-standard cell potential. So the standard cell potential with that superscript 0, and then the non-standard cell potential without that superscript 0. All right, so here on this slide, I'm going to do a little compare and contrast between standard conditions and non-standard conditions. So first, let's take a look at the concentration of the aqueous solutions. So under standard conditions, the aqueous solutions of the reactants and the products are all equal to 1 molar. Under non-standard conditions, at least one of the aqueous solutions is not equal to 1 molar. And now for partial pressure of gases. If there are gases present in the system, then under standard conditions, the partial pressures of the gaseous reactants and or products are equal to 1 atmosphere. But for non-standard conditions, at least one of the gaseous substances has a partial pressure that is not equal to 1 atmosphere. With respect to temperature, under standard conditions, the temperature is 298 Kelvin, but if the temperature is not 298 Kelvin, that would represent non-standard conditions. And then for this reaction quotient, which is a ratio of products over reactants, if Q is equal to 1, that would represent standard conditions. But if you have non-standard conditions, it is likely that the value of the reaction quotient Q would not equal 1. All right, let's take a look at question 8 in the packet. In question 8, it says a student sets up a standard galvanic cell at 298 kelvins with a solid zinc electrode immersed in a 1 molar solution of aqueous zinc nitrate and a solid copper electrode immersed in a 1 molar solution of aqueous copper nitrate. The standard reduction potential for each metal is listed in the table below. So in this table, we see 2 half reactions. One half reaction involves zinc, and the other half reaction involves copper. Now, each of these half reactions is written as a reduction. We need to reverse one of these half reactions in order to produce the answer to part A. So part A says write the balanced net ionic equation for the reaction that occurs when this galvanic cell operates. So we have to turn one of the reduction half reactions into an oxidation half reaction. And if you're not sure which of these two equations should be reversed, remember that when you do reverse a half reaction, you change the sign of the cell potential for that half reaction. And also the sum of the 2 half reactions should be a positive value, because for a galvanic cell, that is a thermodynamically favored reaction, so we need a positive sign for the overall cell potential. If I reverse the copper half reaction, that would change positive 0.34 volts to a value of negative 0.34 volts. And a negative 0.76 plus a negative 0.34 will not give me a positive overall cell potential. So what I know that I have to do to make sure that the cell potential for the overall reaction is a positive value is to reverse the zinc half reaction. So when I do that, that will now become an oxidation half reaction. And the sign changes from negative 0.76 volts to positive 0.76 volts. So in terms of which half reaction I did reverse, it was done in order so that when the two half reactions are added together, I get a positive cell potential for the overall reaction. So for the zinc anode, that's going to be where oxidation occurs, and then for the copper cathode, that's where reduction occurs. So I'm going to go ahead and show you the process. I reversed the zinc half reaction, and I changed it from reduction to oxidation. The cell potential changed from negative 0.76 volts to positive 0.76 volts. I didn't change the copper half reaction, so that remains as written, and that has a cell potential of positive 0.34 volts. So now when I add these two half reactions together, the electrons that are gained in the copper half reaction are equal to the electrons that are lost in the oxidation half reaction, so therefore they cancel out. And here is my overall balanced equation. So it's zinc solid plus aqueous copper 2 plus ions to produce aqueous zinc 2 plus ions and solid copper. And the overall cell potential is 0.76 plus 0.34, which is 1.10 volts. So now, what you see on this slide represents the answer to both part A and B of this question. And if you're wondering if this system looks familiar, hopefully it does, because earlier in the beginning of this video, when I was showing you the general diagram for a galvanic cell, I did use zinc and copper in my example. And you can see on that voltmeter that the overall cell potential for that galvanic cell involving zinc and copper is, in fact, positive 1.10 volts. So again, we now have the answer to part A and B. Let's go ahead and take a look at part C of this question. At the top of this slide, you can see the overall balanced chemical equation involving solid zinc reacting with aqueous copper ions to produce aqueous zinc ions and solid copper. The expression for the reaction quotient for this galvanic cell is written as follows. Remember that with equilibrium constants, it's normally products over reactants. Also, we do not include solids in the equilibrium expression. So for this reaction quotient, Q, it's going to be concentration of the zinc ions, which are a product, divided by the concentration of the copper ions, which are a reactant. But the solid zinc and the solid copper do not appear in the reaction quotient. All right, let's go ahead and answer part C. It says, when this galvanic cell is set up at standard conditions, the concentration of the zinc is equal to the concentration of the copper. Those ions would be a concentration of 1 molar. So 1 divided by 1 is 1, and the initial value of Q is 1. Now, as the cell operates over time, the value of the concentration of the copper ion, because copper is a reactant, will decrease because the reactant will be consumed over time. And the value of the concentration of the zinc ion will increase because zinc is being produced as a product. So as the cell runs, the value of Q, the reaction quotient, gradually increases. That's because the product concentration is increasing and the reactant concentration is decreasing. Now, what about the value of the cell potential as the cell runs? Well, here is the Nernst equation on this slide, and you can see in the Nernst equation, we have that the non-standard cell potential, that doesn't have that little superscript 0 or that degree symbol, that is equal to the standard cell potential minus the ratio of RT over NF times the natural log of Q. Now, you don't have to plug in any numbers into the Nernst equation to realize that as Q gets larger and larger and larger, you'll be subtracting a certain value from the standard cell potential. That means that the non-standard cell potential is going to keep getting smaller and smaller and smaller over time. So as the cell runs, the value of the cell potential gradually decreases. So think about this. What if we continue to have Q get larger and larger and larger? What if, as the cell runs, the concentration of the reactants continues to decrease to the point where there's almost no reactant left, and the concentration of the product continues to increase and become larger and larger. So eventually, not only will the cell potential gradually decrease, but if this galvanic cell is run for a very long time, the value of the cell potential will eventually reach a value of 0. So as Q continues to get larger and larger and larger over time, the cell potential continues to get smaller and smaller and smaller over time. But when it goes all the way to 0, when this happens, now we say that the galvanic cell has reached a state of equilibrium. So at this point, the cell is dead. The voltage, the cell potential drops to 0, and there is no longer a driving force for the reaction. As far as delta G, the value of delta G for a galvanic cell that has reached equilibrium is equal to 0. So we have the initial standard conditions where Q equals 1, and then we have the non-standard conditions, which is what happens naturally as the cell runs over time. So Q gets larger and larger and larger. The cell potential gets smaller and smaller and smaller until eventually Q becomes a very large number and the cell potential equals 0. In part D, it says calculate the value of the standard free energy change, delta G, in units of kilojoules per mole of reaction for the overall chemical reaction that occurs in this galvanic cell. So the two half reactions that were combined together to produce the overall chemical reaction, it was the zinc reaction that we had to reverse from the table. That's going to be the oxidation of zinc. And then we have the reduction of the copper ions. Notice that when these two half reactions are added together, it was 2 moles of electrons lost in the zinc half reaction and 2 moles of electrons gained in the copper half reaction. So for our calculation in part D, we're going to use this equation from the equation sheet that relates the delta G to the cell potential, and N represents the total number of moles of electrons that are transferred in this overall redox equation. So it's going to be delta G is equal to negative, don't forget that negative sign, that's part of the equation, times 2 moles of electrons were transferred, and then times F, which is the Faraday constant, that's 96,485 coulombs per mole of electrons, and then times the standard cell potential, which we determined was positive 1.10 volts. So we're expecting a negative value for the delta G because this is a thermodynamically favored reaction. And so when we do the math, we get negative 212,267. That's when we multiply negative 2 times 96,485 times 1.10. Now as far as the sig figs, the number 2 moles of electrons, that's an exact number. So therefore that doesn't limit the number of sig figs, but I see 1.10 volts for the cell potential. So I'm going to round off this answer to 3 significant figures. We also know that coulomb times volt is equal to joule. So it's going to be negative 212,000 joules per mole of reaction. And if I divide by 1,000, when I go from joules to kilojoules, then my answer would be negative 212 kilojoules per mole of reaction. Again, it's a negative delta G indicating that this process, this reaction that occurs in this galvanic cell is thermodynamically favored. So part E just simply states that. The answer to part D makes sense. Since the reaction that occurs in a galvanic cell is thermodynamically favored, then the sign of delta G should be negative. All right, our next part of this question is to relate the value of delta G, which is negative 212 kilojoules per mole of reaction, to the value of the equilibrium constant K for the overall chemical reaction that occurs in this galvanic cell. So if we know the value of delta G for a chemical reaction, then we should be able to calculate the value of the equilibrium constant for that chemical reaction. So on the equation sheet, there is an equation that relates delta G and the equilibrium constant K. So delta G is equal to negative R times T times the natural log of the equilibrium constant K. Now the R value that you should use is not 0.08206, but rather 8.314, which has units of joules per mole per Kelvin. So the time that you learned how to do this type of calculation was in my earlier video for topic 9.5, free energy and equilibrium. So we're not going from the K value to the delta G, we're actually going in the opposite direction. We're going from the delta G value to the K value. So it's going to be set up where equilibrium constant K is equal to E, and that E is the base of the natural log, and then raised to a power, and that would be the ratio negative delta G divided by RT. So that would be from topic 9.5, free energy and equilibrium. Now here on this slide, this is just a screenshot from that particular video, and in that question from that video for topic 9.5, if we were given the value of K, then we would do negative RT natural log of K. And if we were given the delta G, it would be K is equal to E raised to that ratio of negative delta G over RT. So let's go ahead and do that calculation right now. Watch out for the units. Make sure you use the correct value of R, and then you can go ahead and calculate the equilibrium constant for the reaction that takes place in this galvanic cell. From the earlier calculation for delta G, we have a value of negative 212 kilojoules per mole of reaction. I'm going to use the equation that reverses the process, where on the equation sheet it said delta G is equal to negative RT natural log of K. I'm reversing that process so I can solve for K. So K, the equilibrium constant, is equal to the base of the natural log, E, raised to the ratio negative delta G over RT. Now watch out for numbers, units, and sign here. So notice that it was a negative delta G over RT. So because I have a negative times a negative, that now becomes positive. So it's 212, but look at that, it's 212,000. It's not 212, it's 212,000 because I have joules, and I have to cancel out the joules. So on the bottom, it's RT, that's 8.314 joules per mole per Kelvin, and I have 298 Kelvin for standard conditions, and on the top I have 212,000 joules per mole of reaction. So the joules cancels out, the kelvins cancel out, the moles cancel out, and so when I do this math, 212,000 divided by 8.314 divided by 298, I get 85.6 for that ratio of negative delta G over RT. So we're expecting the value of K to be a really large number here. This reaction is thermodynamically favored, and so it's going to give us a rather large value for the equilibrium constant. E, the base of natural log, raised to the 85.6 power, gives me my answer. So it's going to be 1.5 times 10 to the 37. That's a very large value, but it indicates that this reaction is favoring the formation of the products. So there's our answer to part F based on the calculation for the equilibrium constant. And in part G, the answer to part F makes sense. Since the reaction that occurs in a galvanic cell is thermodynamically favored, then the value of K should be greater than 1. All right, we've answered all the parts of this question, so now I'm going to take a look at that diagram that I had shown you earlier at the beginning of this topic. So in this diagram, we see several different situations, and standard conditions is highlighted in gray in this table, and I'm putting a little blue box around it. So what you see now would be when Q equals 1, we have standard conditions in which the cell potential is equal to the standard value. But if you change to non-standard conditions that cause the system to move closer to equilibrium than standard conditions, now Q becomes greater than 1, and the cell potential is going to be less than the standard cell potential. So if you move closer to equilibrium, Q becomes greater than 1, and the cell potential will decrease from standard conditions. Well, eventually, When you reach equilibrium, now the cell potential drops all the way to 0, and Q becomes very, very large. In fact, it would equal K, which, as we just discovered, is 1.5 times 10 to the 37 for this galvanic cell. So what about if you go in the opposite direction? That would get you not closer to, but farther away from equilibrium than standard conditions. Well, now if Q is less than 1, then the cell potential is actually greater than standard conditions. So if you can move the value of Q so that Q is less than 1, then the cell potential will actually be greater than the cell potential at standard conditions. Now looking at the ratio of products and reactants, when Q equals 1, concentration of zinc equals concentration of copper. So you have the same amount for those concentrations, as in product equals reactant for those aqueous solutions. If Q is greater than 1, it means we have more product or less reactant, or both, compared to standard conditions. So when Q is greater than 1, we have more product or less reactant, or both. Well, what if Q is less than 1? If Q is less than 1, it means we have either a smaller amount of product because something was changed, or we have a greater amount of reactant because something was changed. So compared to standard conditions, if Q is less than 1, it means we have less of the product or more of the reactant as compared to standard conditions. So hopefully this table kind of summarizes the non-standard conditions compared with the standard conditions. Now, we're going to answer question 9, and we'll use the information from this diagram to help us process the concept of what happens at non-standard conditions. So here is question 9. In question 9, it says, a student sets up a standard galvanic cell using copper and tin. The standard reduction potential for each metal is listed in the table below. So just like we did in question 8, we are given two half reactions, and we're going to have to flip one of these half reactions so we can have a reduction and an oxidation occurring in this galvanic cell. So which of these half reactions we reverse is related to that same concept of making sure that when the two half reactions are added together, the overall cell potential will be a positive value. So if I reverse the copper half reaction, then positive 0.34 will change to negative 0.34. And a negative 0.34 plus negative 0.14, that's not going to give me a positive value overall. So I can tell that I'm going to need to reverse the tin half reaction. So negative 0.14 will become positive 0.14. That means that the copper will stay the same. It's going to be a reduction half reaction. The tin will get reversed, and it becomes an oxidation half reaction. So for part A, write the balanced net ionic equation. For the reaction that occurs when this galvanic cell operates, it's going to be copper ions reacting with solid tin to produce solid copper and tin ions. And I'll show you that this is how we process this adding of the two half reactions together. So the copper did not change, so that half reaction remains as a reduction, and the cell potential for that reduction reaction is 0.34 volts. Then when I reversed the tin half reaction, the cell potential changed from negative 0.14 to a value that is now positive 0.14. So I add the two half reactions together, I get the electrons to cancel out on opposite sides of the equation, and my overall cell potential is 0.34 plus 0.14, and that gives me a value of 0.48 volts for this overall reaction that occurs in this galvanic cell. So there's the answer to both part A and part B. Now, moving on to part C, this involves that non-standard conditions, and you can see that coming up in the missing information in this table. We have to decide if the cell potential is less than, equal to, or greater than the 0.48, which was the standard cell potential. So it says, in addition to the standard galvanic cell, the student also sets up 3 non-standard galvanic cells. In each cell, the volumes of solutions used in each half-cell container are identical, and the details of all 4 galvanic cells are summarized in the table below. So cell number 1 is the standard galvanic cell, where the concentrations of the copper and the zinc, the copper and the tin ions are 1 molar each, so Q equals 1, and the cell potential is what we had just calculated, which was 0.48 volts. For cells 2, 3, and 4, we have concentrations that have been altered to give us non-standard galvanic cells. So if I'm doing the ratio of concentration of tin, which is a product, divided by concentration of copper, which is a reactant, it's going to be 0.5 divided by 0.5, so Q equals 1 for cell number 2. For cell number 3, it's going to be the ratio of concentration of tin divided by concentration of copper, and that's going to be 1 divided by 2. So the reaction quotient Q would equal 1 over 2, or 0.5. And then for the cell number 4, it's going to be 2 divided by 1. So concentration of tin divided by concentration of copper, so 2 over 1 is 2. Now I have the value of Q. I have to complete the rest of the missing information by choosing what the cell potential is going to be in that far right column of the table, and it says your predictions should be based on the qualitative use of the Nernst equation. So we're not going to plug any numbers in and solve. We're going to just process this qualitatively using our conceptual understanding of how non-standard conditions will be potentially different than standard conditions. So here, for cell number 2, since Q is equal to 1, that means I would still have the standard cell potential when Q equals 1. So that would be equal to 0.48 volts. For cell number 3, since Q is 0.5, that means that Q is less than 1. That would be a situation where I am now farther away from equilibrium than standard conditions. Q is less than 1. The cell potential should be greater than standard conditions, so greater than 0.48. And then for cell number 4, Q is equal to 2. That's going to take me closer to equilibrium as compared to standard conditions. So Q is greater than 1. The cell potential should be less than the standard cell potential. That's going to be less than 0.48. So no calculations needed, just processing whether Q was equal to 1, less than 1, or greater than 1, and I can make that appropriate prediction about the cell potential for cells 2, 3, and 4. All right, next question is talking about the comparison between galvanic cell number 1 and galvanic cell number 2. It says that each of these cells can be used to power an electronic device. Would galvanic cell number 2 power the device for the same time, a longer time, or a shorter time as compared with galvanic cell number 1? Justify your answer. Now you know that as the cell runs, the concentration of reactants will continue to decrease. Well, look at those numbers for cell number 1 and cell number 2. In cell number 2, we're starting with a smaller concentration of reactants. We have 0.5 molar compared to 1 molar. So we're going to run out of reactants more quickly with cell number 2. So the answer is that cell number 2 would power the device for a shorter period of time. And that's because we start with a smaller concentration of reactant, so the supply of that reactant, the copper ions, will be exhausted more quickly. So smaller concentration of reactants, it's going to decrease more quickly. Eventually, when it decreases to 0, then the cell is dead. So we start with a smaller concentration of reactants. It's going to power this device for a shorter period of time because the supply of copper ions will be exhausted or consumed more quickly. All right, in part E of this question, it says the student observes that increasing the size of the solid tin electrode that is used in cell number 1 has no effect on the value of the cell potential. Explain this observation. And the reason why is because even though solid tin does appear as a reactant, we do not include solids in the expression for Q. So changing the size of the electrode involves changing the mass of a solid. And since solids are not included in the Q expression, Q would not be affected by this change. So the value of the cell potential is not affected by changing the size of the electrode. All right, in part F, it says a student sets up a standard galvanic cell using copper and tin, and the cell potential is recorded as 0.48 volts. Then, a small amount of aqueous sodium hydroxide is added to the beaker that contains the 1 molar copper nitrate. A solid precipitate of copper hydroxide forms in the solution, and the precipitate settles in the bottom of the beaker. How does the formation of solid copper hydroxide precipitate in this beaker affect the value of the concentration of the copper ion in the solution? Justify your answer. So here's a little diagram. You've got your standard galvanic cell, and you can see in the beaker that's on the left, it contains 1 molar copper nitrate. So the concentration of the copper ion is 1 molar. But here comes the change. A small amount of sodium hydroxide is added to this beaker. This results in the formation of a precipitate. So what will happen is that in solution, the value for the concentration of the copper ions in that beaker will decrease because a precipitation reaction will cause some of the copper ions in solution to react with some of the added hydroxide ions. And then now we have solid copper hydroxide at the bottom of the beaker. That means we're removing copper ions from the solution. So the value for the concentration of copper in that beaker will decrease. The follow-up question is, as a result of the formation of this solid copper hydroxide precipitate, the value of Q for this galvanic cell should change how? Well, if the ratio is concentration of tin divided by concentration of copper, we have just decreased the amount for the concentration of copper, and that's in the denominator. So when the concentration of copper decreases, it's going to cause Q to become greater than 1. So we are decreasing the amount of a reactant, and so that ratio now becomes greater than 1. So what happens when Q is greater than 1? Well, according to the diagram, if it brings you closer to equilibrium as compared to standard conditions, when Q is greater than 1, the cell potential should be less than the standard cell potential. So as a result of the formation of the copper hydroxide precipitate, concentration of copper in that beaker will decrease, the value of Q becomes greater than 1, and the value of the cell potential for this non-standard galvanic cell should be less than the standard value of 0.48 volts. Okay, now it is time to move on to our last topic in this packet. This is topic 9.11, Electrolysis and Faraday's Law. Here is an essential knowledge statement from the AP Chemistry course and exam description. Faraday's laws can be used to determine the stoichiometry of the redox reaction occurring in an electrochemical cell with respect to the following: the number of electrons transferred, the mass of material deposited on or removed from an electrode, as in electroplating, the current, the time elapsed, the charge of ionic species, and then this last equation, I equals Q divided by T. This particular equation is featured in this section of the AP Chemistry equations and constant sheet. So I represents the current, Q represents the charge, and T represents the time. Now the current is normally measured in units of amps. The charge is in units of coulombs, and time is in seconds. So 1 amp is equal to 1 coulomb per second. You can also see Faraday's constant, so 96,485, that's the number of coulombs for every 1 mole of electrons. Now, if you look on the unit conversions section of the AP Chemistry equation sheet, you can see that 1 volt is equal to 1 joule per coulomb, and 1 amp is equal to 1 coulomb per second. So on the AP Chemistry equations and constant sheet, I is the current measured in units of amps, Q is the electric charge in units of coulombs, T is the time in seconds. The units of electric current are amps or amperes, and 1 amp is equal to 1 coulomb per second. The Faraday constant gives the relationship between moles of electrons and charge. 1 mole of electrons is equal to 96,485 coulombs. And the relationship between moles of electrons and moles of product formed in an electrolytic cell is related to the coefficients in the half reaction. So if you were converting from silver ions with a charge of +1 to silver metal, or even liquid silver, you would have a 1-to-1 ratio between mole of silver and mole of electrons. But if the charge on the ion were 2+, there would be a 2-to-1 ratio between moles of electrons and moles of metal. And if the charge on the ion, like for aluminum, happens to be 3+, then the ratio would be 3 moles of electrons for every 1 mole of aluminum. And you'll see this in our next examples, that we have to pay attention to all of these details to do these various conversions. So let's go ahead and take a look at question 10. It says, electric current is passed through a solution of molten aluminum chloride, so AlCl3 liquid. A steady electric current of 10.0 amps passes through the cell. The products of the reaction are liquid aluminum and chlorine gas, Cl2, according to the equation shown above. Part A. Calculate the mass in grams of liquid aluminum that is deposited on the electrode in this cell after a period of 585 seconds. So I'm going to start with that value, 585 seconds, and then 10 amps is the electric current that passes through the cell. So, based on the definition of the unit of amp, since 1 amp is equal to 1 coulomb per second, I can set up a conversion factor that allows me to convert from seconds to coulombs. So 10 amps would be 10 coulombs per second. And if I did this math, the seconds would cancel out. Now, I'd like to go from coulombs to something else. Eventually, I'd like to get mass in grams of aluminum. So the next step in the process is to go from coulombs to moles of electrons. The Faraday constant tells me that for every 1 mole of electrons, there's 96,485 coulombs. I'm going to put coulombs on the bottom to get that unit to cancel out. And if I did this math, I would have seconds converted to coulombs and then coulombs converted to moles of electrons. But look at the balanced equation. The charge on the aluminum ion, which is a reactant, is +3. And it's turning into aluminum, the atom, or liquid aluminum, but I have to consider that for every 1 mole of aluminum ions that reacts, 3 moles of electrons are involved in that process. So in this reaction, for every 1 mole of Al3+ ions, there are 3 moles of electrons. That means that in my next step, it's going to involve the number 3. And if you're not sure whether to multiply or divide, put the units in place. It's going to be 3 moles of electrons on the bottom and 1 mole of aluminum on the top. I'm almost done with this calculation because I've gone from seconds to coulombs, I've gone from coulombs to moles of electrons, and now I've gone from moles of electrons to moles of aluminum. So I would go look on the periodic table to get the molar mass for aluminum, and I discovered that there is 26.98 grams of aluminum for every 1 mole of aluminum. So it's going to be 585 times 10 divided by 96,485 divided by 3 and then times 26.98. So my units will be grams of aluminum, and when I do this math, I get 0.545 grams, and I rounded my answer off to 3 significant figures based on the time and based on the number of amps. That was 10.0 and 585. That has 3 significant figures. All right, well now, if that's part A, let's take a look at part B of this question. Part B of this question is actually a reverse of the process that we used in part A. So in part A, we did a conversion from seconds to grams of aluminum. Now we're going to go in the opposite direction. It says calculate the time in seconds that is required for 0.175 grams of liquid aluminum to be deposited on the electrode in this cell. So we're going to start with 0.175 grams of aluminum, and then we're going to just be reversing our steps using the answer to part A as a guide. I will go from grams of aluminum to moles of aluminum using the molar mass, but now the numbers are going to be flipped because I have the grams on the bottom and the mole of aluminum on the top. I'll be dividing by 26.98. Now I have to go from moles of aluminum to moles of electrons. So it's going to be 3 moles of electrons on top, 1 mole of aluminum on the bottom. My next step is to use the Faraday's constant. It's going to be converting from moles of electrons to coulombs. So 96,485 coulombs on the top, and then 1 mole of electrons on the bottom. We still have 10 amps. That would be 10 coulombs per second. I will flip that ratio upside down, so it's going to be 1 second on the top, and then 10 coulombs of electric charge on the bottom. So I just reversed my steps from the strategy for solving part A. So 0.175 divided by 26.98 times 3 times 96,485, and then divided by 10. So units were really important to set up this process. And when I do this math, I get 188 seconds when I round off my answer to 3 significant figures based on the mass that I was given. So with respect to the relationship between units, it's really important to set up your conversion factors and to include both numbers and units so you can keep track of what you're doing. All right, let's go ahead and take a look at question 11. In question 11, it says molten magnesium chloride, MgCl2, can be decomposed into its elements if a sufficient voltage is applied using inert electrodes. As this electrolytic cell operates, liquid magnesium is formed at one electrode, and chlorine gas, Cl2, is formed at the other electrode. A simplified representation of the cell is shown above. The reduction half reactions related to the overall reaction in the cell are given in the table above. Part A. Write the products of the reaction that occurs when this electrolytic cell operates. So we know that one of the products is liquid magnesium. The formula would just be Mg. That's a liquid. And then the other product at the other electrode is chlorine gas, so Cl2, and that's a gas. Now this equation is balanced in terms of both atoms and charge. So we have a total charge of 0 on the right, because those are elements with no charge, and on the left we have 1 magnesium, which is 2 plus, and 2 chlorides, which are minus 1 each. So this equation is balanced in terms of both atoms and charge. Part B. On the diagram above, label each electrode as either the anode or the cathode. So the first step in the process is to decide whether the reaction that is occurring at each electrode is an example of oxidation or reduction. So for the magnesium that's being produced at that electrode on the left, the magnesium is changing from +2 to 0. That means that magnesium is being reduced at that electrode from +2 to 0. So if that's reduction, then the other reaction should be oxidation. So chlorine is changing from an oxidation number of -1 to 0. So chlorine is being oxidized from -1 to 0. That's oxidation. And based on that mnemonic device that I taught you, an-ox and red cat, oxidation occurs at the anode, reduction occurs at the cathode, and that's true for both a galvanic cell and an electrolytic cell like this one. So the cathode is where reduction occurs in this cell, and the anode is where oxidation occurs in this cell. So we've now labeled the electrodes. In part C, write the net ionic equation for the half reaction that occurs at each electrode. So we know what this is now, because at the anode, it should be chlorine being oxidized from -1 to 0. So 2 chlorine ions are being converted into 1 Cl2. And again, 2 electrons are lost. So oxidation involves the loss of electrons, and then reduction involves the gain of electrons. So we have Mg2 plus 2 electrons to produce Mg. Now on the diagram above, draw an arrow to indicate the direction of electron flow in the wire as the electrolytic cell operates. So the flow of electrons in the wire will always go from the site of oxidation at the anode, where electrons are lost, toward the cathode, where electrons are gained. So the electrons will flow from the anode to the power source and then on to the cathode. Now, in the next part of the question, it asks, would an applied voltage from this power source of 2 volts be sufficient for the reaction to occur? But you have to support your claim with a calculation as part of your answer. Now, we have 2 half reactions listed in the table. One of them involves the reduction of magnesium ions to produce liquid magnesium, and that half reaction has a voltage of -2.37. That's the cell potential for that reduction half reaction. The other half reaction is listed in the table as a reduction, but we have to flip that around because we know it's going to be an oxidation. So we have to reverse that half reaction. So now it's going to be 2Cl minus on the left, and it's going to be Cl2 plus 2 electrons on the right. Notice that because we had to reverse that reduction half reaction to make it an oxidation half reaction, we also changed the sign of the cell potential. So it was positive 1.36 volts when it was listed as a reduction. Now it is a negative 1.36 volts because we had to reverse that equation. So if we add these 2 half reactions together, magnesium 2 plus 2Cl minus, to produce magnesium and Cl2, the electrons cancel out, and we get negative 2.37 volts plus negative 1.36 volts, and that gives us negative 3.73 volts. Now, it's okay that this is a negative value because this is not a galvanic cell where the overall cell potential needs to be a positive value. This is an electrolytic cell. So the overall cell potential for an electrolytic cell is actually negative, indicating that the overall reaction is not thermodynamically favored. So the magnitude of this value, that 3.73, that represents the minimum voltage that is needed for this electrolysis reaction to occur. Let's go ahead and read the question one more time. Would an applied voltage of 2.0 volts be sufficient for the reaction to occur? Support your claim with a calculation as part of your answer. So we've just done a calculation that the cell potential for the overall reaction that occurs in this electrolytic cell is negative 3.73 volts. 3.73, that represents the minimum voltage that is needed for this electrolysis reaction to occur, so the answer is no. An applied voltage of 2.0 volts would not be sufficient for the reaction to occur. And as you can see from the calculation, a minimum of 3.73 volts would be needed for this electrolysis reaction to occur. All right, now let's take a look at part F. And this has to do with the conversion, so be careful with your units and your numbers. If the current in the cell is kept at a constant 5.00 amps, that would be, based on the definition of the amp, 5.00 coulombs per second. Calculate the amount of time in seconds that is required to produce 2.00 grams of liquid magnesium. So I'm going to start with 2.00 grams of magnesium. And in my first step, I'm going to go from grams of magnesium to moles of magnesium using the periodic table. Then I will have to turn moles of magnesium into moles of electrons. So I should look at the half reaction to make sure I get that ratio between magnesium and moles of electrons. Then I will use the Faraday constant to go from moles of electrons to coulombs. And then finally, the fact that it's 5.00 amps, that's 5.00 coulombs per second, I will use that information to go from coulombs to seconds. Again, pay attention to your numbers and your units, and that way you can make sure that you put the numbers in the right spot so that the units will cancel out. So here I am going from 2.00 grams of magnesium into moles of magnesium. So on the periodic table, 1 mole of magnesium is equal to 24.30 grams. My next step is to put moles of magnesium on the bottom and moles of electrons on the top. And based on the half reaction involving the reduction of magnesium ions, 2 moles of electrons are involved for every 1 mole of magnesium that's produced. So it's going to be mole of magnesium on the bottom to get that unit to cancel, and 2 moles of electrons on the top. Now it's time for the Faraday constant. I'd like to convert moles of electrons to coulombs. So 96,485 coulombs for every 1 mole of electrons. And then my last conversion factor involves 5.00 amps. That would be 5.00 coulombs per second. But I would like to get the coulombs to cancel out. So it's going to be coulombs on the bottom and then 1 second on the top. So to summarize, I went from grams of magnesium to moles of magnesium using the periodic table. I went from moles of magnesium to moles of electrons using the information from the half reaction. I went from moles of electrons to coulombs using the Faraday constant from the equation sheet. And then I went from coulombs to seconds using my understanding of what amps are. So 5.00 amps would be 5.00 coulombs per second. So 2.00 divided by 24.30 times 2 times 96,485 and then divided by 5.00. And I get a final answer of 3,180 seconds when I round off my answer to 3 significant figures, based on the fact that 2.00 grams and 5.00 amps have 3 significant figures. All right, well now I think we are ready to move on to our next question in the packet. This is question 12. This is also the last question in this packet. In question 12, it says a fuel cell is an electrochemical cell that converts the chemical energy stored in a fuel into electrical energy. A cell that uses hydrogen gas as the fuel can be constructed based on the half reactions listed in the table below. Part A. Write the balanced equation for the overall reaction that occurs when this fuel cell operates. So I'm going to go ahead and just copy down that first half reaction, and I'm not going to change it or reverse it or do anything else. Now take a look at that second half reaction. It said that a cell uses hydrogen as the fuel, and we see hydrogen is actually featured as a product instead of a reactant. So I'm going to reverse this half reaction so I can get hydrogen to be consumed as the reactant, as the fuel. So when I reverse it, I'm going to change the sign of the cell potential from negative 0.83 volts to a value of positive 0.83 volts. And now I have hydrogen gas on the left as a reactant. I also have 2 moles of hydroxide ions. And on the product side, I have 2 moles of liquid water and 2 electrons. Now you can already probably tell if you look at the electrons that the electrons are not going to cancel out. The electrons that are gained in the first reaction, the reduction reaction, are not equal to the electrons lost in that second reaction that I reversed. So I've already reversed it, but now I have to multiply that second half reaction by 2 so I can get the electrons to cancel out. So when I do that, when I multiply the coefficients by 2, remember that we do not change the value of the cell potential by multiplying a half reaction by a constant. So I now will have coefficients of 2, 4, 4, and 4, but the cell potential remains as positive 0.83 volts. Let's see if the electrons will cancel out now on opposite sides of the equation, and yes, they do. There's 4 electrons on the left and 4 electrons on the right. I can also cancel out other things that I see. For example, there's 4 hydroxide ions on the left, 4 hydroxide ions on the right, so they are canceled out. And there's 2 moles of liquid water on the left, and there's 4 moles of liquid water on the right. So therefore, the net difference between the water on the left and the water on the right would be 2 moles of liquid water on the right. I have 2 moles of hydrogen gas reacting with 1 mole of oxygen gas to produce 2 moles of liquid water. So that is the balanced equation for the overall reaction that occurs when this fuel cell operates. And when I added up the cell potential for the 2 half reactions, it would be positive 0.40 volts plus positive 0.83 volts, and that gives me a value of 1.23 volts for the cell potential for this overall equation. It's a positive number, so that means that this is a thermodynamically favored reaction in which hydrogen gas reacts with oxygen gas to produce liquid water. So there's my answer for the balanced equation for part A. The cell potential for the overall reaction would be 1.23 volts. That's a positive number. And now let's move on to part C of this question. As the fuel cell operates for a period of 652 seconds, 1.83 grams of hydrogen gas is consumed. Calculate the average current in units of amps that passes through the cell during this time period. What makes this question a little bit different than the ones you've seen before is that in the previous questions involving current, we were given the amount of amps, but now we actually have to calculate that. So based on the definition, 1 amp is equal to 1 coulomb per second. If we can get the total number of coulombs of electric charge and then divide by the total time in units of seconds, then we can get that ratio. So coulombs per second, that's the ratio that we're looking for to calculate the average current in units of amps. So I'm going to leave the 652 seconds alone for the moment. I'll come back to that. But I'm going to start with the other number I was given, which is 1.83 grams of hydrogen gas. So a good first step when you're given grams is to convert to moles if you know the chemical formula. So on the periodic table, 1 mole of H2 has a molar mass of 2.016 grams when I use the information on the periodic table. And again, this is H2, so it's a diatomic element. That's why it's the atomic mass of hydrogen times 2. Now, if I stop right now, my answer would be in moles, but that's moles of hydrogen. I'd like to get to moles of electrons. So, looking at the overall equation, we can see that 2 moles of hydrogen are on the left, and 4 moles of electrons are on the right. So for every 2 moles of hydrogen that are consumed, there's 4 moles of electrons involved in this process. Now you could simplify that and say that the ratio is 2/1 instead of 4/2, but the math is the same. I'm now going to use the Faraday constant, so 96,485 coulombs of electric charge for every 1 mole of electrons. Remember that amps would be coulombs per second, which means that I'm going to go ahead and do this math, and then I'll take the total number of coulombs and divide by the total time in seconds. So it's going to be from grams to moles. I'll divide by 2.016. To go from moles of hydrogen to moles of electrons, I will multiply by that ratio of 4/2. And then I will multiply by 96,485 to go from moles of electrons to coulombs. So 1.83 divided by 2.016 times 4/2 and then times 96,485. I get a pretty large number. I get 1.75 times 10 to the 5th power. That's the number of coulombs. That's not my final answer, but that is the number of coulombs of electric charge. So amps would be coulombs divided by seconds. So I take the number of coulombs and divide by the total time in seconds. Now this will be my final answer. So 1.75 times 10 to the 5th coulombs divided by 652 seconds. I get 268, and that would be in units of coulombs per second, or amps. So 268 amps, that is my final answer to this part of the question. Okay, well, 268 amps is the correct answer to part C of question 12. So now let's go ahead and take a look at the next question in the packet. This is question 13. And as you can see at the top of this slide, question 13 in this packet was taken from free response question number 3 on the 2024 AP Chemistry exam. Free response questions and scoring information from past AP Chemistry exams can be found by visiting the website that you see listed here at the top of the slide. And then just a brief warning about question 13. Since it is an actual free response question from an AP Chemistry exam, not every part of question 13 will be specifically related to Unit 9. In fact, some of the parts of this question will simply be review of topics that you have already studied from previous units. But when we get to part E of question 13, it will definitely be related to topic 9.11, electrolysis and Faraday's law. All right, let's go ahead and take a look at question 13. Sterling silver is an alloy that is commonly used to make jewelry and consists of 92.5% silver and 7.5% other metals such as copper by mass. Over time, the alloy can form a tarnish of Ag2S solid, that's silver sulfide, when it reacts with hydrogen sulfide, as represented by the following equation. So in this equation, we can see 2 moles of solid silver reacting with 1 mole of hydrogen sulfide gas, H2S, and then the products are silver sulfide, Ag2S solid, along with hydrogen gas. And then part A of this question asks, what are the oxidation numbers of silver in solid silver and silver sulfide? Now, in order to answer part A of question 13, it requires knowledge of things you learned back in Unit 4. So here you can see on this slide, topic 4.7, types of chemical reactions, includes oxidation-reduction reactions, also known as redox reactions. And it involves electron transfer as indicated by changes in oxidation numbers. Also, topic 4.9, oxidation, reduction, or redox reactions, involves balancing chemical equations from half reactions. So an important skill is knowing oxidation numbers. So in my earlier video for topics 4.7 and 4.9, I taught you some rules for assigning oxidation numbers to the elements on each side of a chemical equation. So the first rule says that if an atom is in its elemental form, such as hydrogen, lithium, nitrogen, carbon, chlorine, iron, and it's not part of a compound and there's no charge on the ion, then the oxidation number is 0. So that's what we can see on the left side of the answers for part A, that silver solid is not part of a compound and there's no charge on that ion, so the oxidation state of silver in its elemental state is 0. Now, for Ag2S, that is an ionic compound involving silver ions and sulfur ions. So another rule that I taught you is that the oxidation number of a monoatomic ion is the charge on that ion. So in the examples, if we have sodium chloride, then sodium is +1 and chloride is -1. Or, for example, if we have magnesium oxide, magnesium is +2 and oxygen is -2. So here, on this slide, you can see a periodic table with some charges of ions based on where those elements are located. So group 1 +1, so sodium is in group 1, magnesium is +2, it's in group 2, and I'm highlighting silver and sulfur's location on the periodic table. So where sulfur is located on the periodic table in group 16, it would normally carry a charge of -2 if it forms an ionic compound. So in this case, we have ions of silver that are going to be positive, and then we have the ion sulfur, the sulfide ion, and that's going to be -2. Since I have two silver ions, and they have to balance the charge on sulfur, which is -2, that means that each silver ion is going to be +1. So the oxidation state of silver in this silver sulfide compound is +1. So that's the answer, that the oxidation number of silver in silver, just the element, is 0, but in the compound silver sulfide, it's +1. All right, well, that's the answer to part A. Now let's take a look at part B of this question. In part B of this question, it says, the following table contains the atomic radii for silver and copper. The atomic radius of silver is 165 picometers, and the atomic radius of copper is 145 picometers. So part I of part B says, explain why sterling silver is better classified as a substitutional alloy than as an interstitial alloy. So learning about the properties of alloys, that was from Unit 2. This is topic 2.4, structure of metals and alloys. And you can see highlighted on this slide, the two essential knowledge statements define the difference between interstitial alloys and substitutional alloys. So it says interstitial alloys form between atoms of different radii, where the smaller atoms fill the interstitial spaces between the larger atoms. And so one example is steel, which contains carbon and iron. And carbon is much smaller than iron and can fill in the spaces in between the iron atoms. But on the other hand, a substitutional alloy, that forms between atoms of similar or comparable radius, where one atom substitutes for the other. And the example they give is brass, that contains copper and zinc have a very similar size. Now, on this next slide is from my video for topic 2.4, and I simply define substitutional, formed between two atoms whose atomic radius values are similar, and you can see that copper and zinc have very similar atomic radii values. But with an interstitial alloy, then the atoms have different sizes, and you can see that carbon 77 is much smaller than iron 125. Now, back to part BI. We are not making a prediction about what type of alloy this is. So if you're wondering, how do I know if 145 is similar to 165 or whether 145 is smaller than 165? That's not the choice you have to make, because it says in part BI, explain why sterling silver is better classified as a substitutional alloy. So they've already made the choice for you. So our answer needs to reflect our understanding of what a substitutional alloy is. So we have to talk about the similar size between these two atoms because it's already been classified as a substitutional alloy. And you can see that in my answer to this question, that the values of atomic radii for silver and copper are approximately similar to each other. Therefore, sterling silver is better classified as a substitutional alloy than as an interstitial alloy. All right, well, that's the answer to part BI. Now, let's take a look at part BII. So in part BII, it says, using principles of atomic structure and Coulomb's law, explain why silver has a larger atomic radius than copper does. Now, when you're comparing the properties of two different elements on the periodic table, whether that's ionization energy or electronegativity or atomic radius, this falls under topic 1.7. So all the way back in Unit 1, this is periodic trends. And you can see some examples of periodic trends include ionization energy, atomic and ionic radii or electronegativity, it also requires you to know the patterns of the electron configurations of the atom or the ion. So the first thing I'm going to do is locate copper and silver on the periodic table. Now, they are in the same vertical column or the same group, and that's an important part of my argument. If copper and silver had been located in the same horizontal row or period, then I would be talking about how they have the valence electrons and the same energy level, and I would probably mention how one of them has more protons. But in this case, I don't really need to talk about the protons at all. What I want to call attention to is the fact that they are in the same group and they're going to have different energy levels for their outer shells. Now, you may not remember electron configurations for copper and silver, but you don't need to actually write out the electron configuration. I'm just going to show you the general pattern. So we know that the electron configuration starts with 1s2, 2s2, and 2p6, and so forth. But what you can see on this slide is I'm just showing you the energy levels of the orbitals. So 1s, 2s, 2p, 3s, 3p, and so forth. And so for copper and silver, because copper and silver occupy different periods on the periodic table, then their valence electrons are going to be in different energy levels. So the valence shell of copper would include 4s and 3d. But then silver has an extra occupied energy level. It would be 5s and 4d for silver. And you need to be specific talking about the energy levels. So do not say that simply because size increases as you go from top to bottom down a group, that's why silver is larger. You cannot just simply describe a periodic trend. You have to use principles of atomic structure. So specifically talking about the energy levels of the electrons is part of your argument. Now on this next slide, this is what I had presented in my video for topic 1.7. So if I were comparing the atoms of two different elements in the same period or the same horizontal row, I would mention something about valence electrons being in the same energy level and that one atom has more protons and a greater nuclear charge. But that's not the argument here. Copper and silver are not in the same period, they're in the same group. So when comparing the atoms of two different elements that are located in the same group, you should mention the specific energy levels for the valence electrons. And electrons that are located in a higher energy level are farther away from the nucleus. Electrons located in a lower energy level are closer to the nucleus. So here comes that part about Coulomb's law. According to Coulomb's law, smaller distance between oppositely charged particles, such as the nucleus and the valence electrons, would be a greater attractive force. So I could make an argument for why the valence electrons of copper are more strongly attracted toward the nucleus and would give a smaller radius, or I could argue in the opposite direction, that the silver, those electrons are farther away from the nucleus and have a weaker attraction. All right, let's take a look at the official answer that I have come up with for part B II. Explain why silver has a larger atomic radius than copper does. For silver, the outermost occupied electron level is level 5. So it's a mixture of 5s and 4d. And then for copper, the outermost occupied electron level is level 4. So it's a mixture of 4s and 3d. So I mentioned specifically the energy levels. Silver has more occupied electron shells or energy levels than copper does. The outermost electrons of silver experience weaker Coulombic attractions to the nucleus, and they are located farther away from the nucleus. So I was talking about why silver is larger. You could also talk about why copper is smaller, but I tried to match what the question was asking. So I explained why silver has a larger atomic radius than copper does. So I mentioned specifically the energy levels, and notice that I didn't say silver has more electrons, and I didn't say silver has more electron shells. I said it has more occupied electron shells. That's an important phrase that would be helpful when you're comparing two different elements that are located in the same group or the same vertical column. more occupied shells, and then specifically referring to the energy levels, that would be an important part of your explanation. I know that this is a review of Unit 1, but it's a good thing to talk about as we get closer to the AP Chemistry exam. All right, now you're going to see on the next slide, these are the official scoring guidelines from the 2024 AP Chemistry exam. So for part A, you can see that the correct answer is that silver has an oxidation number of 0 as an element, but in the compound silver sulfide, it's +1. And then for part BI, silver and copper have similar radii, so the alloy would be substitutional versus interstitial. And then for part BII, silver has more occupied electron shells, so level 5, than copper, level 4. The electrons in the fifth shell experience weaker coulombic attractions and are farther away from the nucleus. Now, this is a long question, so this was just simply parts A and B. Now let's take a look at the next part of question 13. This is part C. Now, before I read the question in part C, I'm going to read the information that we are given about the details of an experiment, and we can see a data table is given to us. So it says that the silver sulfide, the Ag2S tarnish on sterling silver, can be removed until only sterling silver remains. A student weighs a tarnished sterling silver sample both before and after removing the solid silver sulfide. So we can see how much it weighs before tarnish removal. It weighs 409.21 grams. And then after the silver sulfide was removed, again, that's the tarnish. So after the silver sulfide is removed, it weighs less. It weighs 398.94 grams. So the student records the data in the following table, and then part C asks, assuming that only solid silver sulfide is removed, calculate the number of moles of silver atoms removed. So let's go ahead and do that calculation to subtract how much did it weigh before tarnish removal, and then minus how much it weighs after tarnish removal. So that difference will be the mass of silver sulfide, Ag2S, that was removed in this experiment. So 409.21 grams minus 398.94 grams, and that equals 10.27 grams of Ag2S, silver sulfide. Now, if you weren't reading the question carefully, you might spend some time looking on the periodic table so you can figure out how much does 2 silvers and 1 sulfur weigh when you consult the atomic masses. So they actually did give us the molar mass of silver sulfide, so we can save some time by simply setting up that conversion factor. It's going to be 247.80 grams of silver sulfide for every 1 mole. So moles on top, grams on the bottom, and now we have our conversion factor, which tells us we're going to take 10.27 grams and divide by the molar mass. So dividing by 247.80, and then we get this particular unrounded answer on our calculator. I think I would round off to 4 significant figures because 10.27 has 4 significant figures. So I would probably estimate this as the rounded answer, 0.04144. Now, there is another detail that many students would miss if they weren't reading carefully. And maybe you've already caught this mistake. This is, in fact, a mistake that I made on purpose because I wanted to call your attention to how important it is to read the question carefully. So right now, I do have a number of moles, but the question says not the silver sulfide, which is what I have right now. It says calculate the number of moles of silver atoms. So many students who were not reading carefully would have stopped right here and simply wrote down, this is my number of moles. But as you can see, this is moles of Ag2S, silver sulfide, but that's not what the question was asking. So the correct answer to this question is not 0.04144. Let's go ahead and set up one more conversion factor. So within the chemical formula, there are 2 atoms of silver for every 1 molecule. I guess you could say empirical formula unit. There's basically 2 moles of silver for every 1 mole of Ag2S. So again, if you weren't reading carefully, you would have missed that step and you didn't multiply by 2. Now when I do this math, I'm not going to get 0.04. I'm going to get 0.08. And again, I wrote the unrounded answer. So I'm now going to round this off to 4 significant figures. So 0.08289. So it's very important to focus on units, and reading the question carefully is part of that process. We now have, on the next slide, the official scoring guidelines for Part C of Question 3 from the 2024 AP Chemistry exam. And this was a 2-point question, so 1 point was awarded for calculating the correct mass of Ag2S, and then the second point was earned for calculating the correct moles of silver. But if students did make a mistake in Part C, it was most likely this important step, that they failed to recognize that the moles of silver is not the same as the moles of silver sulfide. All right, well, that is the official answer to Part C. Now let's go ahead and take a look at Part D of Question 13. Now, as you already know, Unit 9 is entitled Thermodynamics and Electrochemistry. And in this video, which is on topics 9.8 to 9.11, you've already seen lots of examples of electrochemistry questions. So in Question 13, this free response question number 3 from the 2024 AP Chemistry exam, so far in parts A, B, and C, it's been a review of earlier units. So for example, assigning oxidation numbers to elements, or figuring out the structure of an alloy as being substitutional or interstitial, or determining an explanation for why one atom has a larger atomic radius than another, or just simple stoichiometry calculations involving grams and moles. But if we look at both Part D and Part E of this particular question, we can see this is where all of the electrochemistry concepts are located. So in Part DI, we have to write the balanced net ionic equation for plating solid rhodium from the acidified rhodium sulfate. Again, this is an electroplating experiment in Part D. Then we have to calculate the value of the standard cell potential for this process, this electroplating process. And then we have to come up with an explanation for why this process requires the use of an external power source. And then finally, in Part E of this question, which is very much related to topic 9.11, electrolysis and Faraday's law, we have to calculate the length of time in seconds required to plate 2.8 grams of solid rhodium onto a piece of sterling silver if a current of 2 amps or 2 coulombs per second is applied in this electroplating experiment. So again, all of the electrochemistry in this question is going to be in parts D and E. Now let's look at the details of Part DI. So here are the information. Here's the information about the experiment. Rhodium plating is a process used to protect sterling silver from tarnishing. And this involves electroplating, or depositing solid rhodium. And so the elemental symbol of rhodium is Rh. So plating that solid rhodium onto the surface of the metal from an acidified solution of rhodium sulfate. And they also say that oxygen gas is produced during this process. So in Part D, a table of half reactions related to the overall reaction is provided. So we see one half reaction involving rhodium, and then we see another half reaction involving oxygen. So Part DI says the following: write the balanced net ionic equation for plating solid rhodium from the acidified rhodium sulfate solution. Now, if on the AP Chemistry exam you see a question in which you are given a table with 2 half reactions, and you are asked to write the balanced net ionic equation for a particular electrochemical reaction. Now, this could be a galvanic cell, or this could be an electrolytic cell, but if you're combining two half reactions together, you need one of each. You need a reduction half reaction and an oxidation half reaction. So in a table like this, we can see that they are both written as reduction half reactions. So we can't have two reduction half reactions. We can't have two oxidation half reactions. We need one of each. So when you're trying to figure out how to combine these two half reactions together to produce a net ionic equation, one of the first thoughts in your mind is, am I going to leave this equation, this half reaction, as is, or am I going to reverse it? So I'll start with the rhodium half reaction. And again, my question is the following. Should this rhodium half reaction remain unchanged, or should it be reversed? I'll now read the details of this electroplating experiment. It says, this involves electroplating or depositing solid rhodium onto the surface of the metal. So we need rhodium solid to appear as a product in this net ionic equation. So I've now answered my question about should this half reaction remain unchanged or should it be reversed? And the answer is this half reaction should remain unchanged because it says that solid rhodium is formed as a product in this electroplating process. So I'm going to rewrite that equation. I'm not going to change anything about it for the moment. I've just simply rewritten it in the space below. Now, for the next one involving oxygen. Okay, so we have an oxygen half reaction. Again, we're going to have to consider the following question. Should this half reaction remain unchanged or should it be reversed? So you can't have two reduction half reactions added together. And the fact that we did not change the rhodium half reaction, that means it's right now written as a reduction. So one reason to reverse the oxygen half reaction is that you need one of each. I need to turn that oxygen half reaction around to change it from reduction to oxidation. But there's another reason to reverse this equation. Again, look at the details of the experiment. In that last sentence, it says, oxygen gas is produced during this process. So right now, in the equation in the table, O2, or oxygen gas, appears on the left, but we need oxygen gas to appear as a product. So this half reaction involving oxygen should be reversed because oxygen gas is formed as a product in this electroplating process. So what I'm going to do is simply rewrite the equation reversed. And when I reverse the equation, the cell potential will change from positive 1.23 volts to negative 1.23 volts. So as I reverse the equation, I'm going to have 2 moles of water on the left, and on the right, I'm going to have 1 mole of oxygen gas, 4 moles of aqueous H+ ions, and 4 moles of electrons on the right. So there I've just reversed the equation, and I changed the cell potential for the reversed equation, so now it's negative 1.23 volts. I'm not done yet, but that was the important process. You might say, how did I know whether to reverse a half reaction or leave it is? Another way you could have done the analysis, if you didn't get the information about what's being formed as a product, is we need this particular reaction to have a negative cell potential. So why is it supposed to be negative? Electroplating requires an external power source. I'm actually kind of jumping ahead a little bit. We'll see that in part D, III. It talks about explaining why an external power supply is needed. But when you see electroplating, that will have a negative cell potential because it's not a thermodynamically favored process like a galvanic cell or a battery is. So this is not a thermodynamically favored process, which is why we need an external power supply to make this run. Okay, now the next part of the process that will help me to write the correct balanced net ionic equation is to consider the following guidelines that are highlighted on this slide. Now, one of these guidelines I've already done so far. That guideline that says if a half reaction is reversed, then the sign of the cell potential is reversed. We've already done that by reversing the oxygen half reaction. But another important guideline says when combining two different half reactions to produce the overall equation for a redox reaction, the total number of electrons gained should be equal to the total number of electrons lost. But during that process, when you have to multiply each of the coefficients in a half reaction by 2 or by 3 or by 4, multiplying a half reaction by a constant n does not, and that's very important, it does not change the value of the cell potential. Now let's kind of consider where we are right now in this process. I can see 3 electrons on the left in the rhodium half reaction, which is written as a reduction. And I can see 4 electrons on the right in the oxygen half reaction, which is written as an oxidation. So 3 electrons gained, 4 electrons lost. What I'm looking for is the least common multiple so that those electrons are the same. So not 6, not 8, but rather 12. So 3 times 4 is 12, 4 times 3 is 12, and then now this gives me the next step in the process. To get 12 electrons on the left, I'm going to multiply the rhodium half reaction by 4. I'm going to multiply each of those coefficients by the number 4. And then for the oxygen half reaction, 3 times 4 is 12. I will multiply each of the coefficients in that oxygen half reaction by the number 3. And as I mentioned, the cell potential or the voltage does not change. So I am not going to change the positive 0.80 volts. That number will stay the same. And I'm not going to change the negative 1.23 volts. That number will remain the same. So my coefficients in the rhodium half reaction will be 4, 12, and 4 from left to right. And my coefficients in the oxygen half reaction will be 6, 3, 12, and 12 from left to right. So here are the modified half reactions. Again, you can see I did not change the cell potential. It still is positive 0.80 volts for the rhodium half reaction, and it's negative 1.23 volts for the oxygen half reaction. Now, when I add these two half reactions together in this form, I can see 12 electrons on the left, 12 electrons on the right, so I can cross them out on opposite sides. And then when I add these two equations together, I get 4 moles of rhodium 3+ ions plus 6 moles of water. So those are my reactants. And on the right side of the equation, I have 4 moles of solid rhodium, 3 moles of oxygen gas, and 12 moles of aqueous H+ ions. So this is now my official answer to part DI. Hopefully that process of combining those two half reactions made sense to you. And in fact, while I'm still here on this slide, before I take a look at part DII, I've already got 2 numbers on the far right side. Those are the cell potentials that I can add together. So we have to add these 2 values together to get the value of the cell potential for the overall reaction. So positive 0.80 plus negative 1.23 gives me a value of negative 0.43 volts. And then just as a reminder of something I had mentioned earlier about, is this a galvanic cell? No, this is an electrolytic cell. So we actually want the cell potential for the overall reaction to be negative. So electroplating is going to have, in this particular example, a negative cell potential because electroplating is not a thermodynamically favored process. This is not a battery or a galvanic cell. This is an electrolytic cell. The fact that we have a negative cell potential is exactly what there should be for an electroplating experiment. So in fact, what you're looking at is both the answer to part DI as well as the answer to part DII. So part DII says calculate the value of the cell potential for the reaction in part DI. And we've already done that. So that is negative 0.43 volts. That's the standard cell potential for this reaction. Now, moving on to part DIII, this is that explanation about why an external power supply is needed. So part DIII, based on your answer to part DII, which is again a negative cell potential, explain why this process requires the use of an external power source. So this is topic 9.9, cell potential and free energy, and I've highlighted a couple of the essential knowledge statements. Electrochemistry encompasses the study of redox reactions that occur within electrochemical cells. Now, the reactions are either thermodynamically favored, resulting in a positive voltage, or what we have here in this experiment, thermodynamically unfavored, resulting in a negative voltage and requiring an externally applied potential for the reaction to proceed. So the delta G is proportional to the negative or the opposite sign of the cell potential. So if you had a positive cell potential, then that would be thermodynamically favored. But in this example, we have a negative cell potential. Therefore, the process is not thermodynamically favored. So our answer to part DII is that the process requires the use of an external power source because the value of the cell potential is negative. So thus, the process is not thermodynamically favorable. Now, what you should see on this next slide are the official scoring guidelines for part DI. There's the balanced net ionic equation. That was worth 1 point. And then part DII, there's that negative cell potential, negative 0.43 volts. And then part DIII, the cell potential is negative, which means that the reaction is not thermodynamically favorable. So 3 separate points were awarded for part DI, II, and III. And now we come to the last part of this question, which is part E. All right, in part E, the instructions say calculate the length of time in seconds required to plate 2.8 grams of solid rhodium onto a piece of sterling silver if a current of 2 amps, also written as 2.0 coulombs per second, is applied. Now, we're only given 2 numbers in part E. We're given 2.8 grams of rhodium, and we're given a current of 2.0 coulombs per second. The 2.0 coulombs per second, that is a conversion factor. That would not be a good number to start with. In fact, I would like my final answer to be in units of seconds. So I'm going to save the current for a conversion factor that I will do at the end of my set of conversion factors. So a good number to start with would be 2.8 grams of rhodium. To give you a general overview, we're first going to have to go from grams of rhodium to moles of rhodium. So we can use the periodic table to do that. Then we're going to have to convert from moles of rhodium to moles of electrons. And I've left the table of half reactions on this slide so you can see that there is a relationship between moles of rhodium and moles of electrons. Now, once I get to moles of electrons, I will use the Faraday constant to go from moles of electrons to coulombs of electric charge. Then I can use the current, 2.0 coulombs for every 1 second in my final conversion factor. So it's very important as you're setting up your conversion factors, use your units. So strong emphasis on units. Don't just start multiplying or dividing numbers together. So I'm going to be very clear with how I put my units in my conversion factors. Okay, so my first conversion factor, let's go from grams of rhodium to moles of rhodium. And when you look on the periodic table, you can find the atomic mass or the molar mass of rhodium. And so that is 102.91. So there's 102.91 grams of rhodium for every 1 mole. Now I need to get to moles of electrons. And you can see in the half reaction that is listed here in the table, there are 3 moles of electrons for every 1 mole of rhodium. So moles of rhodium on the bottom, moles of electrons on the top. That's why it's important to use your units and your conversion factors. Otherwise, you might not know, am I multiplying by 3? Am I dividing by 3? So I'm definitely going to multiply by 3 so I can put moles of rhodium on the bottom and moles of electrons on the top. Now, looking back at the answer to part DI in this question, this was our balanced net ionic equation in part DI. So in fact, you might say that there's 12 moles of electrons, but there's also 4 moles of rhodium. So had you written the conversion factor like this, 12 moles of electrons for every 4 moles of rhodium, you would still have the correct ratio. So 12 over 4 is the same as 3 over 1. So either of these conversion factors would still give you a 3-to-1 ratio between moles of electrons and moles of rhodium. So now we're ready for the Faraday constant. So the Faraday constant is 96,485, but that is coulombs of charge for every 1 mole of electrons. Again, look at the units. Moles of electrons are now going to go on the bottom, and then coulombs of electric charge goes on the top. The only thing I have to do now is apply the current, which is 2 amps, or 2.0 coulombs for every 1 second. And I would like seconds to be on top and coulombs to be on the bottom. So my last conversion factor puts 2.0 coulombs on the bottom to get those units to cancel out, and then 1 second on the top. So very clear, I'm going from grams of rhodium to moles of rhodium to moles of electrons to coulombs of electric charge, and then finally from coulombs of electric charge to seconds, or time, so time in seconds. When I do this math, I get 2.8 divided by 102.91 times 3 times 96,485, and then finally divided by 2. And this is my unrounded answer. 3,937.8 seconds. Now that's a lot of significant figures. Considering that I started with 2.8 grams of rhodium, that number only has 2 significant figures, as well as my current 2.0 coulombs for every 1 second. I'm going to round off this answer to 2 significant figures, so I'm going to write this as 3,900 seconds. I could also write this in scientific notation as 3.9 times 10 to the third seconds. But on the next slide, you'll see the official scoring guidelines for Part E of Question 3 from the 2024 AP Chemistry free response question. So this was a 2-point question in Part E. So if the student got as far as moles of electrons, that would earn them the first point. And if they went all the way to seconds, then that would earn them the second point. And that was broken up into 2 parts. That way you could get some partial credit. So the final answer is 3,900 seconds. All right, well, Part E of Question 13 was the last part of this question. So now we have come to the end of this video. I hope that you found all of these answers and explanations helpful. Thanks for watching.